Looks like we're live, I hope. Let me get into the screen here and see if everybody hears me and sees me. Do you hear me? Do you see me? Hi, everyone. I am a one-woman show, as you all know, and so things sometimes take a little bit longer than I'd like them to. You are live, audio good. Yes, wonderful. Hey, Nick, thank you. Mike, thank you so much for being here. Everybody be very nice to Mike Richardson. He is a moderator and he will keep you honest. So everybody's here to learn and in an encouraging environment. And if people are saying, hey, your comments are driving me nuts, please slow down or stop, then please behave. Please be nice. Don't make Mike work too hard because he will kick you out. Wonderful. Everything good audio. I see Nick. I see Metal Halo. I see Andy. I see, what is that? Projecto Cart? Wonderful. These are neat names. Bill, thank you. All of you. Wonderful to see you. Chris is in the house. That's great. Thanks, guys, for coming in. We are, yes, as you can see, I did dare this time to actually use Carrington class event in the title. We'll see how that works. It's kind of a little bit of an experiment. Last time, if you recall, for the A1 class, I called it Space Weather Events in the 20th Century and Beyond. The reason why I decided to put Carrington class events is not just because it's an experiment, but also because, as it turns out, we are only going to be talking about Carrington class events in this particular class. In some of the others, which will follow on, we'll see events that really had impacts that were Carrington class-like, but they weren't necessarily Carrington class events. And so that's kind of the attitude I'd like to be able to, or not the attitude, but just the introspection that I want you to be able to do, and the perspective I want you to start thinking about when it comes to these massive superstorms, and why I may be the only person, sadly, on who is on YouTube doing forecasting who doesn't freak out when it comes to Carrington class events. I look at them and go, yeah, they're big. Okay, they're big. Because there's just so many things. It's not just one thing. And so we'll start today by reviewing a little bit of what we did last time to kind of refresh our memories. And then we'll jump into, well, we won't do that. Not if my computer decides to go to sleep. We'll jump into the 1972 event in August, okay? Probably I bet many of you don't even know that there was an event in August that was a Carrington class event. And no one thought that really we haven't had anything nearly as large since, 1859, right? That was the big one. Not true. We deal with Carrington class events all the time. They hit us all the time. And sometimes, actually most of the time, their impacts are nothing like what you would expect. Okay? So that's kind of in a nutshell what we're going to be doing today. And hopefully by the end of this course, if you haven't seen the first one, you'll jump back to the first one because the first one was a lot of fun. Albeit I looked back at how my behavior was, and I will apologize. I was maybe a little bit snarky in the last class, just because I think, mainly because there were so many people that just look at me like, Carrington class will destroy us and wipe us to the dark ages. She didn't know what she's talking about. And so I think during part of that class, I got a little bit, how you get sometimes? And so I'll try to be a little bit more accommodating to those who really are super, super frightened of these events and really think that every YouTuber on the planet is absolutely right, that, we're going to be, we might as well give up the ghost now, right? Just go to, some mortuary and pick out your coffin now. You might as well, right? While they're still good, while there's still enough, there's a selection left, and you don't have to get the 99-cent special, right? Because everybody's going to die 2 seconds from now. No, that's not the way it is, and I don't want you to think that, but I'll be more accommodating to those people who haven't quite let go of that, that fear yet, okay? So before we begin, I want to, of course, thank all of my, let me put this in big screen so that I can, so that I can show you properly. I want to thank all of my VIP steering committee. You guys are just so fantastic. These are people who steer the ship for me, with me, as this community continues to grow and as we get more recognition and more really more opportunities to bring space weather, proper space weather awareness to the public eye. Excuse me, I'm shedding. These are the people that help me decide what is the right course of action. Where do we go from here? What is super important? What should be kind of, what I should step back from? And they've saved my life more times than I can count. So all of you, you know who you are. Thank you so much for everything that you do. And if you want to get involved, I don't know if I have any VIP steering committee positions open right now, but if you're like someone who really, really, really is dying to be a VIP member, let me know and we'll talk and I'll see what I can do. And so thank you again for all of these, and also my super VIPs. You guys are, the Radiant Star, the highest tiers. You guys have personal contact with me, one-on-ones all the time, and I just can't thank you enough for all you do. And if you notice, Matthew Shipley's up here. He's got his own YouTube channel, so pay attention. He's doing excellent stuff, and he fills in the gaps, especially when I'm not around, because I don't do this every day, right? Because I can't. Now, my mini course patrons, thank all of you again for so much for everything that you do. You are the reasons why these courses are happening, right? I wouldn't be able to do them without you. I've spent just this past week, while the sun was sleeping, basically, I've spent this past week just scouring for information on different events. And it turned out that I found such a wealth of information that I really wanted to share about the 1972 event, far more than I realized was out there. That's why this whole class is going to be about the 72 event. And it's going to be comparing to modern day. Okay, so we're going to have some comparisons here and there to give you some really thought-provoking understanding of really the difference between these events and the kinds of events we see on a daily basis, right? The difference between the rainstorms and the hurricanes. So thank you, all of you, for being here and continuing to support. And you also, of course, can veto if I say, hey, I want to teach about this, and you guys go, nah, I don't want that. You have the right to veto, but you also have your right to get your questions answered first. So thanks again for all of that. And yes, I will do YouTube subscriptions soon. I promise. I just haven't done them yet. Okay. Oh, that's interesting. So to begin, you try to get things doing this the right way, and stuff just gets messed up. Okay. There we go. Now the title's not covered. Okay, so just checking to make sure nobody's saying anything. Thanks, Vince. You so see you, hear you. Excellent. Just checking to make sure nothing's wrong. And hello, everyone. Okay, and I will, just so you know, when it comes to these courses, this course is going to be about 3 hours. Okay, all my courses are about 3 hours, and it's because you're supposed to take it over the course of a month, because I do them about once a month. I know I've had to skip the last couple months, and I apologize for that, but the sun just got so busy. Other things happened. It just went so crazy that I just didn't get a chance to, because I've got to do a lot of research for these particular courses, and because they're advanced topics, right? So when you watch these courses, don't feel that you have to take the whole thing in at once. Please feel that you can take a break. And when I pause for Q&A, that's a wonderful time to get up and take a break, because I'll typically do a Q&A for about 10 or 15 minutes or so before I jump into the next part of the course. So definitely don't feel badly if you can't take it all at once. It's kind of drinking from a fire hose at times. So I understand that. But yeah, it's going to be, this will be a long one. We've got a lot of charts to get through. I'll try to do them faster than I normally do. Okay, so last time, just to review, because we're going to do a little bit of a review to kind of get your feet wet and remind you of how we looked at things, how we kind of define Carrington class events. In public eye, when we talk about a Carrington class event, these are the types of things that people say are definitions of a Carrington class event, right? These are the massive solar storms that literally are akin to mega flares, or they're called a kill shot. Some people call them micronovas, not everybody, but some people don't know the difference between a Carrington class event and a potential micronova that basically would incinerate the entire planet if our star were even capable of doing something like that. Okay. One of the reasons why you know a micronova hasn't really happened is because our timeline of life on Earth would be very different if micronovas were a common thing. We've learned a lot since since science started and solar physics started back in the 1750s. And some of the things that were written about even in the 20th century are definitely we've debunked them. So just because something is scientific doesn't necessarily mean, and a PhD wrote it back 100 years ago, doesn't necessarily mean it's true today. Science improves, and we know when we're wrong. So these are definitely not Carrington class events. Power grid killers, okay, it depends upon how you want to talk about that. Armageddon from the sun, God's wrath, right? Basically anything that spells doomsday for Earth's weakening, or for Earth's weakening magnetic field and all electronics on Earth, no matter how big or small, right? These are emotional based, right? And we talked about what pictures in the public domain look like. I mean, I even saw some just insane pictures from a very scientific, a reputable scientific periodical just the other day, and they were just insane. They had the power lines lighting up just like this, and I was like, oh, not again. Please don't stand under power lines during a Carrington event and try to look for the sparks or the light, because they're not going to light up like neon glowing stuff. It's just not going to happen. And it's definitely not, the sun focusing a micro, a magnifying glass on the sun like we're ants on the planet, and it's going to just send a beam of energy, focused energy, to the Earth. This is just not how it happens. This is all emotional, okay? But there's good reason for why this type of emotional-based definition of a Carrington class event, why it's there. Right? And not all of it is pop culture. Not all of it is insane drawings and fantastical representations and Hollywood mock-ups. Not all of it is that at all. Some of it is quite common, is quite scientific in nature. And where are you? There you are. In fact, here's one. Make sure I get the volume off here. Here's one that I may have shown. I think I've shown this before when I talked about, I think back when I did the magnetospheric, the M courses, and I talked about the second chef in the Earth's magnetic system. I might have shown this particular NASA video, and it's a neat video because it's very instructive. So here's the Earth's magnetic shield, and I'm in the way, I see. So this, let me pause it real fast. Boop. Okay. So here's Earth's magnetic shield. We're looking at it from the side. So the sun is this way, pointing like this, okay? So the solar wind is coming in like this. And all these lines that you're looking at are magnetic field lines, okay? So this is the Earth's magnetic system. And as I've talked about many times, the core of this magnetic system is a slinky, right? So if I take this slinky and wrap it around for those who are not familiar, if I take the slinky and I try to aim it kind of like this, there we go. So that's kind of the way it is, all right? It's sitting, this cute little donut is now sitting like this, and it's the inside of this thing. And you can see how these magnetic field lines wrap around and get bigger and bigger and wrap around in here, okay? That's the core of the Earth's magnetic system. It's basically a dipole field. And you can see the Earth right here. So that part of the slinky actually sits inside. So the Earth sits inside this slinky, okay? Not completely inside, it's like halfway out. But at any rate, the inside of this structure typically is robust, and it doesn't change very much because all of the battle, so to speak, when it comes to these big solar storms is being fought out here. And the job of the solar storm, whether it's strong or not, the job of the solar storm is to take this, the field, magnetic field right here of the Earth's, the front end, right, the front lines of the Earth's magnetic system, and peel them back. Peel it back like a banana, like a fruit. Just open these field lines and fold them back, okay? So when a solar storm hits Earth, what happens is that the stronger the solar storm, the more lines it can peel back. And as it peels it back, you see this goes to this, goes to this, goes to this, goes to this. So you can do what's called eroding flux. That's the scientific phrase for it, right? Weak storms hardly erode any flux, okay? And I'm not going to go into the details as to what all this means and what the implications of it are. But just for suffice to say, the more that you can erode this flux, the more aurora you get at the poles, and the further down to the equator, basically the bigger the oval gets, and it can come all the way down to the equator if you erode a lot of flux, okay? So it's always the day side flux that's eroded, okay? and it peels, and it doesn't eat these things. These don't go away. These field lines just break and connect to the solar wind, and then they fold back this way. And then when the solar storm's over, they come back and reconnect, okay? So you're not destroying anything. You're just, it's like hair being blown back in the wind, right? You have bangs typically, but in the wind, they all get blown back. Same kind of idea, okay? It's just magnetic. And there are, you know, other rules related to it, but same kind of idea. And that dictates how much aurora you get, that you see, and that dictates a lot of the currents going on. It's, you know, it's a very dynamic system, and this magnetic system is what causes a lot of the currents that we see on the ground, right? So for power grids and everything else, that's the thing. So weak solar storms don't do much, and you'll see, I think this is the version that has, are you going to play? Oh, you are, okay. So a weak solar storm hits, and you see it erodes some flux. I'll stop, boom, okay. It eroded some. You see how small, much smaller that is? This red is just density, so you're seeing the storm hit. You can see it kind of crush this thing in. It is smashing into it a bit, right? It compressed it a little bit, and now it's eroded. So you see a lot of stuff, a lot of these magnetic field lines being folded back into the tail, okay? Very common. This is a standard, decent size, not huge, but decent size event. I think they'll label what one it is. Don't they say it? Letting it go a little bit long. Oh, wait, no. Come on, tell me which one it was. Is this the Bastille Day event? But you can see it from the side. I'm sorry, I probably should explain this. So now you've tilted it so the sun is coming in kind of at an angle, right? So if I'm the sun, I'm kind of facing away from you, staring at the earth, right? But it's still coming in at you this way. So now you're looking at the north-south extent. The equatorial plane is a cut right through here, okay? So that's what you're looking at. And so just showing another plane, you can even see, now they're just zooming in, and you can see, you'll see some of these field lines kind of flip back, and then some will begin to flip forward. That's just the ballet. See, there's some flipping forward. And you can see them as they flip back forward and reconnect, and they're reforming, okay, all that frontal lobe, okay? And that's when the solar storm is kind of waning. And I think they show the date. Don't they show the date? So you can see it softening, and so the field is kind of opening up again, and it's eroding. See, it's now back to something nice. Okay. Now they may show the date down here. If they show a date other than 1859, you know it's not. Well, you'll know immediately when you see the 1859 event. Okay, it's going to look very different, right? So they're going to set it up here pretty quickly. And where I want you to watch when the 1859 event happens is, okay, hold on. Looks like they're doing it again. This is not the 1859 event. This is maybe a stronger event. You can see there's a little bit more flux being eroded. So we'll wait for it, because I know the 1859 event is in here. How long is this video? Oh, you're not even letting me. You poop. All right, maybe they'll show it now. It's coming. Oh, that's okay. 2006. So this was probably December 2006 event. All right, here we go. You ready? Okay, not yet. So here's the event from a scientific modeling perspective, right? This is a model that's been infused with data. So it's a magnetic model, right, that's got physics in it. And then they input the solar wind data from the 1859 event, or at least what we think it was. We had to do some forensics because we didn't have satellites in the sky in 1859. So we have to kind of do some forensics to kind of reimagine what the solar wind conditions must have been to get the type of impact that we got on the ground. So here's what the Earth's magnetic system looked like just when things were beginning. You can definitely tell that there was stuff going on because you're seeing these, what are called plasmoids, these big jets of plasma being shoved down the tail. The reason for that is that there's so much energy being pumped into the system that it's got to shoot stuff down the tail just as it shoots stuff up here to cause the aurora. It's trying to exhaust all this extra stuff, right? The Earth's magnetic system's going, because it's got so much junk in it, and it's got to exhaust it somehow. But the big bad boy hasn't really hit yet. Okay, so here's the frontal lobe, right? Looks really reasonably pristine, pretty large. Here's what happens. Boom! What happened? Where's the lobe? Where'd it go? it eroded all the way down. I mean, you can see like what, 1, 2, maybe three little field lines in there if you really grab a magnifying glass, okay? It almost eroded completely the front, what we call the dayside flux. This, to somebody who doesn't understand what's going on, looks like a planet incinerator, okay? And I fully agree with that. It looks like a planet incinerator. Guaranteed, if you're eroding flux down to this level, likely the radiation belts are gone. Because you can have radiation belts on this side, but when they come to this side, there's no jail. There's no magnetic jail to hold them. So it just dumped them. I mean, it flushed the whole radiation belts out. I wouldn't be surprised, okay? Guaranteed, this came inside of geosynchronous orbit. But here's the funny thing. When you lose that much flux, your satellites, your geosynchronous satellites are actually sitting out in interplanetary space. And if nothing else is going on, it's just a solar storm, there's no radiation storm or anything with it, well, they're probably loving life. This is why Stereo A and all the other ones that have been hit by Carrington-class events go, meh, no big deal. Because all the business, all the heavy-duty business is what's going on in the Earth system. Because it's the Earth system that makes things a lot crazier. But at any rate, this is pretty daunting. And it's scientific. Right? So even the scientists, even the scientific data and the models that we show really set people up for, oh my God, this is a nail biter. If this hit Earth, we're in trouble. Let me let this play out so you can watch it. Look how fast the machine gun. Watch it. It's just, as soon as it hits, look at it spitting out here. It's just doing plasmoid ejection like literally rapid fire. So they show it 17 different ways from Sunday, so you can see how incredibly intense it was and how much frontal flux it eroded. And remember, all that stuff is just blowing the bangs back, right? It's just blowing it back to the backside or the far side of Earth. And NASA then, does its cute little closing and go, hey, wasn't that cute? Now, scientists will go, wow, yeah, that's impressive. But a layman, a non-expert, is going to go, it's Armageddon. This is exactly what a mega flare is, and a planet killer, and a micronova, and a power grid killer, and an Armageddon, and it's God's wrath, and I mean, it just goes on and on and on and on. Right? So that's part of the problem with Carrington-class events, is that even the scientific sources can be interpreted in such a fashion that to a non-expert, it looks like it supports the idea that we're all going to die. But it doesn't. It's really not that. So how do we then? Right, so that's why I did this last time. I crossed this off and said, this is an emotion. This is touchy-feely. You can't really define a Carrington-class event based on this. And this is what we talked about last time. We spent the entire class talking about this. So how do you do it? What do the scientists do? Right? Do they do it by eruptive signatures on the sun? Right, for CMEs, for coronal mass ejections, or perhaps in situ signatures with the interplanetary coronal mass ejections, as they come out and we actually look at them and they pass over us. What do we see? How big are they then? Right? Do we do it by solar flare signatures? The big, because these are going to be eruptive, big, energy expelling things. So guaranteed there's going to be a big solar flare along with the coronal mass ejection. That doesn't happen with smaller ones, but it can happen with the big ones. It always happens with the really big ones. So do it just by the solar flare. So you see an X45, and so you assume that the big CME coming out is going to be a G5 level storm, a massive, planet killer. No, right? Maybe, maybe not. Do we do it by radiation storms? The particulate radiation signatures, solar energetic particle events? Because that's another side of things, right? We talked about this last time. Do we do it by effects at Earth? Because not every single one, as you see, not as you saw last time and you will see again, not every event has all of these things. Some of them have really insane aspects in one category, but not in another. And the event that we're going to talk about today is exactly that. And it turns out defining a Carrington-class event from a quantitative perspective is far trickier than one might expect. And it's actually not as likely from the perspective of having something match that 1859 event. But by the same token, because as we talked about with the 1859 event, and I think I'll show it in a minute, maybe I'll show it now. Oh, yeah, I'll show that in a minute. As we'll talk about, the 1859 event had a lot of different markers, of these markers, that it got high marks in. Is that right? Markers that got high marks in. Okay. It was exceptional in multiple categories, but not every Carrington class event is. So it only takes one of these signatures to have something be labeled a Carrington class event, typically, even in scientific vernacular. But it doesn't necessarily mean it's going to give you what you think it's going to give you. And it doesn't always mean that you're suddenly going to have an 1859 planet killer. It just doesn't happen. Okay. So that was what we spent all last time talking about. And I brought up one of the big papers that I love, was written by my old advisor and Janet Lumen, who are really good friends of mine. And of course Pete, who has had one of his claims to fame is a paper that he wrote talking about something like a 12% chance of a Carrington class event here in the next 12 years. And that was, I think 12 years ago. And you know, I knew that when that got picked up by the press, it was going to be this crazy thing. And people were going to run with it, and they were going to get that they were not going to interpret it the way it needed to be interpreted. Because the type of Carrington class event that Pete was talking about was not a planet killer. He was just talking about a Carrington class event that could have any of those particular categories. And that is still true, but it doesn't mean it's going to have massive effects at Earth. So I believe that this paper that they wrote ended up being kind of a response to that. And it showed some very interesting things. And we talked about this last time, right? I'm not going to go too much into it. We focused on the Carrington class event and kind of how this whole plot worked, where you're looking at almost 3 different types of Carrington class events, which we don't really understand yet. There probably is a continuum, but it's hard to say because we're seeing these things fall on a particular line here, a line here, and then potentially a line here. And I'm not going to go over the details. If you want to know more details about what this is all about, please see the last course, the A1 course, because this is A2. But if you look at this, and this is a plot of distance, the transit time. So when it's launched, from the moment it's launched, how long does it take to hit Earth? And then this is the distance, what we call the observer flare distance. And I talked about the cone angle last time, where if you have, you could have a sunspot on the sun or a bad actor on the sun. And it may not be in the right position to fire something right at you. If it's on the east limb, the gun is going to be firing over here, and it's going to take longer for something to reach you because it's not firing direct at you, right? Or if it's even down south, right? Or let's say it's on the west limb, but it's north, so the gun's over here. I mean, how often do you get a gun that's going to be firing straight at you? Obviously, that's going to be the best way of getting nailed. But obviously, there are some Carrington class events. We've had guns, back in 2017, we had a Carrington class event hit Earth where the gun was fired here. We didn't even know it was a Carrington class event unless you looked carefully at the data. You didn't even know, because the effects at Earth was nothing. Why? Because the gun wasn't pointed at you. But the idea that you can point a gun that far away from you and have the dang thing still hit you, that tells you how big that event was. It got us to a G1 like that, but it only lasted 6 hours because we were just on the hairy edge of it. So it just barely nicked us, and it got us to a G1 instantaneously. That's how massive and crazy this was. This was September 10th when it was launched. It was the second, well, probably the biggest solar flare of solar cycle 24, but it wasn't in Earth view. So it was partly occulted. So it officially registered as the second largest flare, but it was bigger. So this explained very well that just because a Carrington class event is launched doesn't mean it's launched at Earth, and doesn't mean when it hits Earth it's going to, just from logistics, doesn't mean it's going to hit Earth and cause a disastrous thing. So from a certain perspective, Pete was very right, because if anything, we had almost 3 Carrington, 2.5 to 3. Well, one of them is debatable, whether or not it was a Carrington class event during solar cycle 24. We saw 2, if not 3 of them. So today, we're not going to talk about this one, which actually wasn't the fastest. Let's talk about the fastest one. How about that? Oh, I forgot about this. Yeah, and speaking of Carrington class events, back in, and this is a terrible rendition because it moves so slowly, but back in March of this year, as I talked about last time, we actually had a far side eruption that looked very close to Carrington class. This was one that actually had a radiation storm that was launched with it that was so massive it actually hit Earth. I mean, it was 360 degrees. That's how big the radiation storm was. It blew us away. But yeah, potentially a Carrington class event or something close. On the far side, didn't hit us. But let's not talk about that. Let's talk about this one. This is the fastest one on record. This happened in August of 1972. It was a set just like we've talked about many times. When you have a bad actor on the sun, it just fires as soon as you see it. As soon as it either emerges or rotates into view, it's angry, and it fires off a solar storm and a solar flare and then a radiation storm and another solar flare and another big solar storm, and it just keeps all the way across the Earth-facing disk until it disappears on the sun's far side. Okay, so that means when you get Carrington class events, typically from an active region, you don't just get one event, you get a barrage. Okay, and that's part and parcel of what we're going to see today. Even the 1859 event, actually there were multiple of them, but the one that hit us and actually caused as much ruckus as it did wasn't a single event. It was actually a combination of two ICMEs that hit Earth and caused the ruckus it did. Even the 1859 event, I believe, was two. So 1859, the 1989 event, which I don't even think is on this list. Yeah, it was October 1989, but where's March? Nope, March isn't on here. But that's one of the biggest effects that we've ever seen with, or at least it changed, it moved the needle when it comes to space weather, maybe potentially more than any other event has since. Okay, so hopefully I've really drummed this into you. I don't know why this is lowercase. I should have made this all capitals. There is no single definition for a Carrington class event, right? The reason why the 1859 event did so well is because it had so many different markers in there that were amazing. It had a big sudden ionospheric disturbance, meaning a magnetic crochet. It had a massive solar storm impact at Earth. It had a big radiation storm impact. It had a huge, because it was a very fast-moving CME or solar storm. It had a big Forbush decrease and depression. I think this might actually be. This actually might be. Oh, that might be a magnetometer. Yeah, that's magnetometer. But it had amazing aurora, right? It had, of course, the telegraph operators being shocked. So we had massive GICs, geomagnetically induced currents. It just every single marker it was stellar. Now, was it number one? As we'll see in a sec, no, it wasn't. It wasn't number one in any one category other than, I believe, radiation storm for certain particles. But because it did so well, as I talked about last time, it was on the podium. It medaled. It may not have taken the gold, but it took the silver in many categories. And so that's why we remember it and why it is a benchmark event. But not even close to the fastest. 17.6 hours is when it took, how long it took to get to us. This one that we're about to talk about today took less than 15. Could you imagine seeing a solar flare on the sun and having less than 15 hours before the thing hits you? Insanely fast. So you think, oh my Lord, right? That was going to be pushing us to the dark ages. That's going to be aurora clear down to Singapore, right? Lasting for days. You'd think, right? Well, let's find out. Oh yeah, and here's, probably should have put this one first because it was what I talked about. So here is the kind of the podium. Here's how the medal, this is the Carrington class event Olympics. I just thought of that. I probably should change this to that. I'll call this from there, from now on. The Carrington class event Olympics. As you can see, the 1859 event, really it was only particles, solar energetic particles, where it did very well. The sudden ionospheric disturbance, the magnetic crochet, where the solar flare was so intense that it actually caused an impact in the ionosphere. It lit up the ionosphere so much that it actually caused us to read it in magnetic field changes on the ground. That was actually a Halloween storm. Is that Carrington? Really? Well, depends upon your definition. Right? For fast solar wind, here we go. Boom, that's our event. Fastest. Okay? Which a lot of people think is the only thing that matters. No, it doesn't. Geomagnetic storm to actually cause aurora wasn't even the Carrington class event. It wasn't even the original Carrington event. It was 89 in 1941. And for aurora, 1872. Okay. Which tells you it was pretty big considering. We didn't have cell phone cameras back then, but it got down to 19 degrees in latitude. Okay. So, ready? Are there any questions about that review at all before we jump into the actual new parts of this? Let's see. Oh, huge internet problem. That's no problem, Myers. This will be archived. For those of you who don't know, this will be archived on on YouTube. The link that you used to get here will stay. So and it will be put in a playlist in the Carrington class events, the A series of courses, A for analysis. So you'll see it. It's not going away. Let's see. Any questions? Singapore Aurora is a good name for a band. It's true, because it's rare. That's neat. I like that. Hey, host, in that one, your body was in the green screen. Yeah, my body is in the green screen. Right. So, not really sure what you mean. The text is blurry. Oh, can anyone else read it? Oh my gosh, I hope so. I hope you can read it. Are you guys having problems seeing the text? I hope not. If that's the case, then there's an issue with the internet connection, but hopefully not ours. Oh, great. Hi, Jerry. Good to see you. Very welcome. So everyone, Jerry Ryan is also a moderator, and be nice because he will boot you if you're being rude, and he's a wonderful guy. So and for anyone who's asking questions and I don't see them, if you ask them to, a lot of times they get frustrated, just ping one of the moderators to say, hey, can you boost my question so that I can see it? Because I always focus in on them. So, oh good, okay, no, so text is good. All right, so yeah, whoever is having that, I didn't see who it was, you might consider jumping off the stream, maybe rebooting your computer and starting again, or just check your internet connection, or plug in an Ethernet cable, so that might help. Because it looks like everybody's okay here. Okay. Oh, okay, good, Laura, good, you did solve it. Excellent. Thanks, guys, I appreciate the all clear, literally. Okay, guys, so ready? Shall we jump into it? Here we go. Oh, and I will tell you, a lot of the text, just so you know, not every event that we are going to analyze in the future, in future classes, will be this black and white. And I mean this literally, because this is 1972, you will have to deal with a lot of black and white print and a lot of black and white figures because we don't have the benefit of, even in some cases, computers. We're looking at very old data. We're also looking at very old imagery from before, when we didn't have any space telescopes. We had OSO 7 back then, and that was hardly getting going. So you will notice that in the analysis. So when I say black and white, I literally mean black and white in terms of figures, not so much in whether or not the definitions of a Carrington class event are clear. So it's kind of ironic. At any rate, so this was the beginning of the space age, really, was early August, early 1972. We had just launched OSO 7. It was literally the first CME hunter, because it was a chronograph that we launched. We had a chronograph on the spacecraft that we launched in space, and we were literally looking for space weather from space for the first time. So we hardly knew at that time, we were hardly aware or convinced, rather, that solar wind existed. Now, granted, Eugene Parker, had written his paper back in the 50s, but he was laughed at for a very long time. It took more than a decade, if not several decades, to really have people be convinced that the solar wind did flow from the sun all the time. So there was a lot of argument at this point as to what CMEs really were, how they worked, right? And we had really very little clue about how all of this stuff fit together. So I kind of had a giggle when I went back and I looked at some of the papers and what things people were thinking back then, because it's so much clearer now, right? But science progresses, and some of the biggest names in space weather, you'll see their names here because they were just legendary in how much they advanced the science. So here is the McMath region. This was region 11976, and it was ugly. This is a view from Big Bear Solar Observatory. We had a really nasty filament that came through here. So for those of you who are used to looking at calcium imagery, here is a white light image that I managed to find. I wanted to get the Mount Wilson drawings of this, and sadly their site is down. Their archive is down. So Ulrich, we need, please get your site back up, because we need those archives. But I wanted to be able to get a drawing so I could show you this in a little bit better light. Plus the fact that this observation is rotated relative to this one, but for the life of me, I can't figure out. I've tilted this thing all sorts of different ways to try to align them exactly the same. I think this is the filament down here, right here, but I'm not sure. It could, the filament might be right here. And I look at this and I'm like, how in the world? So this may be at a slightly different time when they were taken, because maybe if a solar physicist says, Tamitha, good Lord, rotate it like this. For some reason, I just couldn't paste it together. So these are not completely aligned. They look a little bit different, but they are the same region. And this was done in white light, and this is done in I think, calcium line. And then you see, here are images where you could actually see on the ground, believe it or not, from the Paris Observatory, you actually saw the white light flare. Okay. And that's not common. This is the same thing. This is what Richard Carrington saw, something very similar, right, where he was actually able to draw the flare ribbons because he saw them. That was the first time it was ever seen. But white light flares are pretty uncommon, right? And you can't see flares from the ground typically unless they're done in white light because the atmosphere absorbs them. This is why we have to have space telescopes. So that was the region flaring at the time. And it let off not just one, because it was a very bad actor, as you can imagine. It let off 4 extraordinary, massive flares, right? It let off a lot more than 4, but 4 extraordinary ones. We had 2 of them on August 2nd. These were X-class, and they were white light flares. We had one on August 4th, which was over an X20 plus with gamma rays. And we had one on August 7th, was also X-class and white light. Okay. And I think the August 7th was the worst one. But we had our instruments saturated. We couldn't really tell how massive they were. And then there was also a disappearing filament, which I think was this one. So, if you want to know more about it, this is straight from Dolores's paper, which is a very famous paper. And we'll get into why it's so famous. But she had to have she looked into some papers, into some work that was in reports that were declassified. So she was able to get a better feel for just how incredible this event was. And I don't think a lot of people knew about this event. And we'll talk about why that is. How can you have a Carrington-class event hit Earth and nobody knows why? Not until basically 2018, nobody knew. And the only reason they knew is because of the impacts that were beforehand. Well, we'll talk about that. Okay, so this was a very ugly region. And let's talk about the ionospheric disturbances, right? So if I go back, let me, because I want to, and because I put this together, I might jump back and forth between certain things, right? Because we have all these different signatures to dive into. So how are we looking at it? So in this case, we're going to be looking at solar flare signatures. Let's start there, right? Now I probably should have, now that I think about it, but I had so many charts that I was putting together that I did not actually put in a solar flare, like an X-ray flux chart. And the reason why is because the X-ray flux went up and then it went off scale. And then it came back down, and it was like, well, that's not very useful. It just kind of disappeared. So why don't I try something else? Why don't I try another way of describing these solar flares? So here is an old paper published. This was published in a compendium of works that were done by NOAA, actually, back in I think late 19. It was maybe the early 1973 that it was published. And so it was just this like a proceedings, probably from like a big workshop. And it was all about impacts of the events in 1972. And I found this quite interesting. This was Knuth et al. And we're looking at just ionospheric effects. I've never seen them drawn this way, but this was quite interesting. So this is on, these are two different frequencies. As you can see here, this is 2.6 megahertz. Okay? Remember, we used a lot of HF back then. So this is the main way we communicated back in the 70s. This is 25 megahertz. Okay? So you had two different effects. Now what we're looking at is a time of day. Down here you can see 4, 6, 8, 10, 12, right, to 18 to UT. And the reason why it's not the whole day is because, I mean, you can only, this is just the time that you can actually see the sun. And so what they're drawing by this baseline is really what the ionosphere looks like and this is sunrise. And it goes up to noon, so this is when you're the zenith angle. They're probably drawing the zenith angle. Oh, they're drawing dB, okay. I think they're drawing scales of dB. So it's not zenith angle, but I've seen it many times where it's a zenith angle. But this is basically the noise level, and it's going to be peak at noon, right? And then it's going to go back down as the sun gets lower in the sky, and then, of course, it sets, and so you have no more. So this, they're showing days. So this is August 1st, I believe. No, this is August 2nd. The writing is so small in these. No, this is August 1st. I am correct. August 1st. August 2nd, August 4th, I believe, and then August 7th. Yes, okay. So at 2.6, just under 3 megahertz, right? These are lower frequencies, but basically right at the hairy edge of the HF band. We're looking at fades on the first. On the second, massive fade, right? Basically, this frequency was unusable till noon. On the 4th, again, unusable for a good portion of the morning and a little bit later. And then on the 7th, usable except at this point, and then not usable for the rest of the afternoon. Okay? And so they're showing where these things are occurring. And at 25 megahertz, right, they're actually showing impacts where it's more usable because the higher frequencies you have, the more usable they are. When you have a big solar flare, you can, I mean, in this case, the fade, in this case, the amount of, this peak of this thing is just so off scale, they can't even register it. How many dB down, how much dB of noise are they getting from the sun? These were happening during the solar flares, the big solar flares that were occurring. And even when you jump up to 25 megahertz, if you go to August, this is August 4th, yeah, you're still seeing, you know, unusable to a great degree, especially in this region for this period. You have this much noise on the bands. And again, on August 7th, look at this one, just off scale. And they're saying it's 9.5 dB down. And this was the largest that they had ever seen with the August 7th event, the August 7th flare. Okay? So much so that when they looked at what they should expect the heights of the ionosphere to be, here's August 1st, August 2nd, August 4th, and August 7th. Okay? You see again, kind of dips, because these flares are large. So they're seeing the impacts to the ionosphere. Right? Today we have the DRAP model that shows us when the D layer is being, when the upper atmosphere is being ionized. Right? And so you're seeing not only just a shift, because you can see where in the dashed line, you're seeing where the normal ionosphere would be. Now remember, this is for the F layer or what it was. But you can see how it's kind of gotten out of round where you'd expect it to be and it's not. Or here's where you expect it to be and it's actually shifted compared to where they're. So they're doing ionosons and they're checking to see where the height of the ionosphere should be. Right? So a little shifting from solar flares, right? A little shifting. Look at this. Look at the 7th. That height of the ionosphere dropped from like what they're expecting is around 70 something, 78, and it dropped down to less than 60, 66 or something. They said they'd never seen that before. The last one that they had saw was 1968, was more than 10 years prior to that, and it didn't come down as far. So this was a big event back then. It was like, oh my gosh, look at this. And this, to our, to today's standards, wouldn't mean like all that much because we don't really use HF except for amateur radio, right? HF is not our common way, and VHF isn't our common way of communication. But way back when, it was. It was a standard way of communication. It was also how we did our radio, typical radio. We did even television. VHF and UHF were frequencies that were used quite commonly. And so these types of massive solar impacts really wreak havoc with that type of communication. Here's the record-breaking magnetic crochet from this event. Magnetic field on the ground, if any of you remember when we talked about magnetic field from magnetometers, when we talked about H, D, Z, and F. These are basically orientations. You have height, you have a horizontal component and the declination, and you have these components where if you look at the magnetic field, and this is the Earth's magnetic field coming in, and you look at how it's wiggling or changing, there are things that can cause that change. And typically it's a big geomagnetic storm. It's like what I showed you in that movie, where you've got a big solar storm coming in and it racks the front of the Earth's magnetic system, and then it peels the flux back, and then the whole thing just rocks and rolls. And so down on the ground you see all sorts of your magnetic field where it's coming in and anchoring itself to the Earth. You're seeing a lot of horizontal movement, a lot of just the direction is just wiggling like crazy. And again, if you want the details of these angles and all of that, then you can go to I believe it's the East course series, where you're talking about ground magnetometers, and we dive into all of the details of this. But that's not where this course is, so I'm not going to jump back into that again. Needless to say, right, we're not going to be looking at the vertical component, which is the Z component. We're looking at the H component, which is the horizontal component, because that's the one that wiggles parallel to Earth's ground. And that's the one that really causes induction of currents in the ground. Okay, so just not, in this case, not from a big geomagnetic storm causing the Earth's magnetic field to wiggle, but from our upper atmosphere being lit up like a Christmas tree thanks to all of this junk and the new ionization layers that are bringing things way down, and you've got this massive change really, really quickly. That induces currents. That induces magnetic field changes, because you've got suddenly a bunch of charge that wasn't there before, and it's being put there because of a huge blast of ionization. It's just ripping the electrons right off of the neutral atmosphere, and so it's causing this charge layer. Well, that's current, basically, and that's going to and that's changing current, and so you're going to induce a magnetic field, and that's what you see. Boing! This is from our atmosphere causing this, and you can see it here. Massive, very, very big. 50 gammas, 50 nanotesla is a big change, and you can see it here. From two different, in nearly the same location, two different places, two different spacecraft, I think ATS-3 and ATS-5, I don't remember. This is ATS-5 over here, over here. This is ATS-5, and I think this is ATS-3. So they're doing occultations, they're getting signals through the ionosphere to tell how much things have changed. And they can see, I believe that was how they did it, how they can see the ionosphere, the magnetic crochet in there. So, and this one is total electron content. They were actually measuring it directly, which is, I believe, what they're doing here, measuring it directly. And then this, of course, a magnetometer on the ground. So, big event in terms of solar flare. So yes, it scores really highly in solar flares. Is it number one? No. If I go back to the number one event, that's actually one of the Halloween events. It had bigger flare than that. So, and this is what we call the SID, the sudden ionospheric disturbance. What does this do to radio communications? Messes them up. What would it do to GPS? Mess it up in that area, if you're anywhere near the subsolar region. Yeah, not subsolar, yeah. Be careful how I say that. Anywhere near high noon, it'll mess it up. But it'll probably, in this case, it'll probably mess it up anywhere on the day side. You could have big problems because you're not just going to have that magnetic crochet. So I've got to be careful. I can't separate out the effects because they all happen. That's the problem with space weather events, right? You can't just separate one effect out and say, oh, well, it's only going to do this, because there's always all these other things that are occurring. So if we're having a magnetic crochet like that, guaranteed we're having a radio burst that's going up to gigahertz. And of course there was. There was a radio burst in this event that went up over a gigahertz. Okay. So I guess I can go back. So that's the solar flare stuff, right? So let's I wish I had like this pinned or something so I could keep going back. So what about, you know, we didn't have eruptive signatures necessarily because we didn't have any space-based instrumentation to look at them. But we could see when the thing hit Earth what the ICME. So we couldn't see the CME necessarily because we didn't have any observations. But we could see, in a sense, as soon as that ICME hit, what happened? Like, how did the Earth respond? So we can get an idea of you know, of how intense that particular ICME is. And on top of that, we actually did have a couple satellites out there that I'll show in a sec that gave us some idea of the data. Excuse me, I'm being distracted because my husband's class is getting in. I keep getting notifications that are driving me nuts here. And if you hear them, they'll go away in a moment. It just happens to be near 11 o'clock. Okay. Oh, shoot. No. Where was I? Right. There we go. Okay. So it turns out that despite the fact that we were just barely starting the space age, we did have a couple satellites or spacecraft out there. In this case, this was satellites. These were the Prognos 1 and 2. These were Russian satellites that were in a polar orbit going around. And they were in a polar HEO orbit, which meant that they came way out, super high, out of the Earth's magnetic system, and then dove back in, and then came way out again. And as these satellites were way out, they were taking measurements of the solar magnetic field. I mean, the solar wind and whatever not magnetic field, but whatever was hitting us in terms of plasma. And so, okay. And I should have put this second, but we'll see Pioneer 9, not Pioneer 9, pardon me. These were actually at Earth, okay? And what they registered was solar wind speeds that jumped up to over 2,000 kilometers a second. That's insane. So this CME, which took 14.6 hours to reach Earth, had an average transit speed of about not quite 3,000 kilometers a second. I mean, that is, for anyone who knows what an average CME speed that we have today, right, in the last cycle or two, we're sitting at 500 kilometers a second. A super fast one might be 6, maybe, I don't even know if we saw one that was 700 kilometers a second, let alone something close to 3,000, right? I think it's 2850 as you see here. And by the time it reaches Earth, because it's decelerating, because guaranteed it's the fastest thing out there, so it's coming up against traffic on its way to Earth, and so it's slowing it down, right? But even that, it's pushing all the cars out of the way. Imagine a big tank with a big bulldozer front on, you know, big snowplow front, and it's just pushing the cars out of the way as it goes. Of course, it's going to slow it down a bit, but obviously it didn't slow it down that much if it's still over 2,000 kilometers a second by the time it reaches Earth, right? But imagine the pile of cars that must have been in front of it. And in this case, there not only was a pile of cars in front of it, so to speak, there was another CME in front of it that it slammed into. So we actually had a big, massive thing in front of this thing before this shock even hit. Okay. But as you can see, it took a few days for it to calm down, right? Because, I mean, even as it goes past Earth, it's still sitting. 2 days later, it's still sitting at over 800 kilometers a second. 2 days later, the thing hits about, you know, late on the 4th, and 2 days later on the 6th, it's still going over 800 kilometers a second? What? That's unbelievable. I mean, that really tells you how massive this structure was. So at any rate, massive density enhancement. But here's the weird thing. you would think that this would be the planet killer, right? This would be the thing that would knock us back to the Dark Ages. Anybody who's familiar with DST, it only got to minus 125. What the heck happened? This thing should have been a minus, like a Carrington class event. I keep saying it that way. The 1859 event had a DST arguably of over minus 600 to possibly over 1,000. It depends upon how you do the analysis. Some people have the peak of that storm being minus like 12 or 1,700 nanotesla for, so an order of magnitude larger than this. How in the world do you have, if this is the fastest thing out there, how in the world do you have that happen? We'll talk about it in a minute. Okay. Here's Pioneer 9 observations. And this was a neat little analysis because what you're looking at in this diagram. Now remember, these are very old papers, so these are all hand drawn, right? This is what I mean by everything's going to be black and white today. And I don't mean by clarity, I mean literally black and white. So we're looking down at the sun from the North Pole. Here's Earth way over here. Here's Pioneer 9, okay? It was flying by this way. If I got the dates right, yeah. Here's August, okay? August 1st, August 15th, I believe. So here's August. Here's about where it was observing. And this is what it observed. And I almost took time to draw in lines so you could get, more of a feel for these cute little data points. But this is, welcome to data collection in the 1970s. So this is, if I can remember, this is, I think, the angle of the magnetic field at the time. This is the strength of the field here. Okay. This is the speed of the field. This is these particles. This is the energetic particle event, which we will talk about in a little bit. These are the solar protons from the solar energetic particle event that was actually ongoing as well. Remember when we talk about when you have a bad actor, it unleashes everything at you all at the same time. This is why it's so difficult, especially with big events, to separate things, because it's all just, you're just getting George Foreman to death, right? Just boop, 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 just getting you. So, and then this down here, what is this? Particles, this is Explorer. Okay, so this is the solar energetic particle event from Pioneer, and then this is from Explorer, which was, in certain cases, it was out of the Earth's magnetic system. I think I have a diagram that shows Explorer a little bit later. These are reasonably comparable, but we're not going to focus on this bit yet. We're just going to focus a bit on here. As you can see from the speed, that's the thing that says U. The speed here, I hope you can read this. Maybe you can, probably can't. It says 900. So these are, I can't even read it. 100, 300, 500, 700, 900. Okay, that's what the numbers read, right? So here's the speed of this thing, up here. Why they did this, I don't know, because I can't read that. But that's about 1,000. Okay, so even at Pioneer 9, way over here, this structure, which was launched out this way, which I'll give you a visual aid in a sec. Even way out over here, this thing was moving over 1,000 kilometers a second at Pioneer. Okay. It was moving at 2,000 kilometers at Earth, 2,000 kilometers a second at Earth. So, wow, right? This whole structure was spanned more than 0.738, as you see here. It says 0.738 AU. That's how wide this thing was. And likely, it was more like this. And yes, that's a cute little banana. It's in its cute little hammock. I didn't draw the hammock, but it's a slinky that goes something like this. So so I got a slinky, and it's got both feet that hit the Earth, but oh man, my slinky is disappearing on the white. I paint the slinky white so it sticks out on the green screen, but now I can't put it against white because it disappears on me. So I'm holding it. You can't really see it. Maybe I should have made my banana a different color. So the slinky is kind of going like this, but then the legs of the slinky come back to the sun. This leg goes back to the sun, and this leg goes back to the sun. Right, so they'll go back to the sun, but they spread out, and I don't have enough arms to be able to really make the slinky look good and make it look like you need to see it. Okay. But that's kind of how the slinky would be if, if it would behave itself, and, you know, it would be like that. And so you have this slinky coming all the way out, coming out like this. And yes, it gets flattened and elongated because of for two different reasons. First, it's plowing into the solar wind, and that's slowing and distorting it, but it also is expanding in a spherical geometry, so it's going to expand out like that. So that's oftentimes how they look. So as it moves from Earth, or from Pioneer to Earth, right, you see that it's going to be hitting Earth, which is now underneath this structure, at a much, make sure I have my finger at Earth, here we go. So there's Earth, and as it moves out, it's going to be hitting Earth in a place that's a little bit closer to the apex. Whereas at Pioneer 9, it's hitting the flank of the structure, right at the edge. If I go back to Pioneer, right, it's hitting here, whereas Earth is hitting somewhere about here. So it makes sense that you're going to be seeing something that is going to be much faster if you're going to be closer to the flank than closer to the apex than the flank. But if you look at the McMath region where it was on the sun when you had the big white light flares, it was just east of center disk. So this is just a cartoony way of kind of giving you a feel for really what was happening. But it shows you also how wide this structure was, that it was able to be seen at multiple places. Sadly, we didn't have very good, if any, magnetic field orientation data. We have this here, but it's not very useful. Not as useful as it should be, and we don't have it from the other spacecraft. We don't have it from Prognos 1 and 2. We just have the plasma density. So too bad we can't do some forensics to get a better idea of the structure of this thing, the wide, the multi-spacecraft structure, because that would have been neat to be able to have done that. One thing you do need to notice, this is the magnetic field strength, 5, what is this? 15, 25, 35. Right here, that is the highest magnetic field. We're only sitting at about 38, maybe 40 nanotesla. Not, whoops, up here. Not the most intense magnetic field strength. But then again, we're also viewing the flank. Much stronger at the apex, likely. Okay, so with that, knowing that it's the fastest structure out there, and it's quite large, right? And it's running, it's over 2,000 kilometers a second when it hits Earth, and still moving at over 1,000 kilometers a second even on the flanks. You know this thing's going to pack a wallop, and sure enough, it did. What we're looking at now are the Forbush decreases. Now, if those of you who remember my CME courses, you will remember my teachings on Forbush and Scott Forbush and how Forbush decreases were discovered and what they meant. What Forbush decreases are, in a nutshell, are basically neutron monitors or ionization chamber measurements of cosmic ray showers as they come into the Earth's upper atmosphere. And we have a background flux of this stuff. It's like a soft rain all the time. And it creates just noise at a certain level. And if you have neutron monitors, you can count them. You can actually see this information. However, and where this stuff comes from, it's not coming from our star. It's coming from all the other stars, right? So this is the stuff that our sun actually saves us from during solar maximum. It tries to shield out all this stuff. But some of it still gets in because it's extremely energetic. And so we bathe in this all the time. But when there's a big structure like this, it creates, well, yeah, you can almost see it. It looks like an umbrella, doesn't it? Okay, here's the handle. I'm holding it, put it up like this. I'll sit under here like this. How's this? Does that work? Okay, shield me. That's what's happening. Okay, so it's shielding us as it passes over Earth. It's shielding us from those cosmic rays for a short while. We get caught in the magnetic bubble or the umbrella that is the magnetic field of the CME. And our cosmic ray fluxes go down. The bigger the shield, right, the stronger the magnetic field, the stronger the structure, the deeper drop that we experience. The interesting thing is that when we had this hit, we had, and part of what also shields us is not just the magnetic bottle, but also the shock wave. So the strength of that shock wave. And the shock wave is what drives, is kind of like that snowplow. And I've talked about this before when we talked about coronal mass ejections. You know, it's kind of like a sound wave, just like when you're in the upper atmosphere and you're having planes or jets rather that are flying faster than the speed of sound. They have to create a shock wave to be able to move that air. You have to change the air literally in front of the plane, because the air moving at subsonic speeds, or with the air moving the way it is, it can't get out of the way in time before it gets hit by this plane. So when a plane is moving then faster, in this case, than the speed of sound, what happens is that a shock wave forms, and that shock wave literally slows down. The purpose of that shock wave is to make energy transfer, energy exchange. And you slow the speed of that air down relative to the plane. You slow it down, you heat it up, and you make it much more dense. And the reason why you do that is that, first of all, you have to get rid of the energy of the speed. You have to divert it somehow. So you divert it by obviously you're slowing down the particles, but you heat. You cause heat to build. And as you slow the particles down, they have to bunch up. But what that does is it allows now the particles to divert around the plane in time so the plane doesn't smack into them, so the plane can keep flying through. But that's how shock waves are created. And that shock wave literally fundamentally changes the characteristics of the air or the fluid that it's in order for an obstacle to get by it. Same thing happens at our bow shock in front of our planet as the solar wind blows by. We have a standing bow wave, a standing bow shock that causes those particles of the solar wind. It changes the nature it changes the characteristics of that solar wind to allow it to divert around us, around our planet. And with coronal mass ejection, same kind of thing. So when I talk about this, I'm just showing the banana, but believe it or not, in front of it, there's a big shock wave. And the stronger the shock wave is, the wider it gets, the more intense it gets, and the better shield it is for shielding out cosmic rays. So because of the speed of this structure, when it hit, it jumped way down. Now we've got two different, do I have that right? Yeah, that's South Pole. Two different shock waves, or two different neutron monitor observations. One in Japan at very low latitudes, and one at the South Pole, very high latitudes. And the reason why I wanted to compare them is because the signatures are slightly different. And I aligned the figures so that they basically lined up with August 3rd, August 4th, August 5th being the same, August 3rd, August 4th, August 5th. So all the way to the 10th in the top panel, 10th goes to the 10th in the bottom. Okay, so the events are lined up and they're, you can compare them apples to apples. So in the Japan one, you can see the shock, the Forbush decrease jumps way down here. I mean, this is a massive decrease, right? And then it comes up very, very quickly. And as a matter of fact, it peaks a little bit and then comes down and then goes back up, okay? This peak and this peak here are not very big, but these are actually ground level events from the radiation storms. Japan at low latitudes were shielded very well, so the ground level events are not very large. You can almost not notice them. South Pole, that's, at the pole, right? Last time I checked, South Pole means pole. And so it's an area where our magnetic shield is open. And so particles are able to just really penetrate very easily. Well, the ground level events, as you can see, are taller than they are in Japan. Makes sense, right? So that's why you see them bigger. But the Forbush decrease is actually much more intense at low latitudes than it is at high latitudes. So it shows you automatically the impacts of even a Carrington class event are very different depending upon where you live, right? These Forbush decreases, granted, are very big, but very different and the ground level events are very big, but very different. Right? You actually have a much more intense impact near lower latitudes than you do at high latitudes. A lot of that has to do with what we're, let's see, am I going to talk about it yet? Yeah. A lot of that has to do with what's going on with that magnetic shield. Okay. So when a big event that's super, super fast like this, with a big shock, smacks into you, what you experience is definitely latitude related. And you can see, you can have very intense impacts at low latitudes compared to high latitudes, depending upon what is the phenomena that you're looking at, and what is the cause. So here we are conditioned to think that an impact at Earth, any impact at Earth from a Carrington class event is going to cause aurora, and it's going to be horrible all over the poles, and then it's going to go down to the equator, because we're going to have aurora that's going to expand downward, and anything at high latitudes is going to be impacted the worst by far. And that's not always the case, especially when it comes to these really fast guys that have what I will lovingly and probably get pelted with olives for calling a bumper car effect. Okay, we'll talk more about that in a sec. Low latitudes are extremely susceptible. And what is the bumper car effect? Well, it's an EMP. That's what we're looking at. We're looking at this. We're looking at the effect of an EMP. Okay. Now, I don't mean it's the direct effect. So let me be careful when I rephrase that. You're looking at the manifestation of the shock hitting and the CME slamming into Earth that causes this. But what else does that do? Okay, so this is the period of the EMP, not necessarily caused by the EMP. So when you have a CME that slams into Earth super hard, super fast, before you even worry about eroding flux, right? I mean, that's when I go back to that movie and we think, oh, immediately, there goes the flux. It's all dayside flux is completely eroded. Everything's folded to the night side, and now, all hell's going to break loose, and it's going to rain cats and dogs, and everybody's going to get aurora, and buildings are going to catch on fire, right? People are going to go to the hospital, right? Great. That is the fear-mongering side of a big geomagnetic storm. But just because you have a Carrington class event, does that mean you're going to get a big geomagnetic storm? Or perhaps any geomagnetic storm? Are we beginning to see that maybe no? Right? We already talked about how DST did not drop very much at all. Minus 125, heck, we had worse than that just a few months ago. The G3, if you remember from our first class, we had a G3 and G4 level storm. Did we have a G4 or was it G3? Back in February and April, March. When was that? I still have it, I think, in this packet. It's just put in the back. Do you guys remember this? I talked about these dates. Remember this? Remember me showing aurora in Perth and aurora in North Carolina? Remember this? New Mexico aurora? Phoenix, Arizona aurora from March? Amarillo, Texas aurora? Do you remember this? Here's Nebraska, right? Southern Arizona again. This is April. These storms had DST of minus 125, possibly higher. I believe higher, actually. I mean, higher, should say that carefully, lower, right? Because DST is minus. Here's Stonehenge. Guys, this was just back in April. Okay, so if that's the case, and I'm not going to show them all. If you want to see them all in a more intense, we saw aurora in China. Remember that? If you don't believe me, here it is. China. Okay. if that could occur from a G3, then what in the world are we looking at here? What is making this particular storm so intense? And why can Carrington events, if it's called a Carrington event, and we're seeing that it definitely is one, right? It's the leader. It takes the gold when it comes to speed. Why in the world is it so much weaker when it comes to geomagnetic storms? And how could it have caused the problems it caused? Well, it is the speed. In this case, it's the speed. So when a massive event that's moving very, very quickly hits Earth's magnetic shield, the very first thing it does, before it even has a chance to peel the flux back, it compresses, right? We've talked about this where we show, and I wonder if I still have the movie up. Oh, I don't? Bummer. I could pull it up, but I won't. It takes the Earth's magnetic system and it slams into it, right? And because the Earth's magnetic system is a spring, it's very compressy. You can squeeze it. And as you squeeze it, you shrink it, right? If anybody who knows E&M, electricity and magnetism, knows that magnetic fields can be squeezed. And how we define, or not define, but how you notice that is through when we draw magnetic fields. We'll draw them, if it's a weak field, we draw the field lines very far apart. But as we squeeze them together, the lines get closer together. Well, that shows that the field strength is going up because the field lines are closer together. So that's how we draw it to kind of give us, but it's the same kind of idea. It's almost like density going up, right? You push things closer together, you're going to get more magnetic field strength, right? Because you've got more flux in the same location. So that's the first thing that these big solar storms that are super, super fast do. Even before you can say, is it going to trigger a geomagnetic storm? The first thing it does is compress. Well, what happens when you compress a magnetic field? Well, you change it. Uh-oh. Anybody who knows Maxwell's laws knows that's trouble. Anytime you change a magnetic field in time, anytime you change, any magnetic field change with respect to time will create and induce an electric field somewhere. Okay? And in this case, it reduces it on the ground. And the faster the change, the bigger the induction of electric field, which means currents. The faster you can create and the stronger currents you can create in the ground. That's just the fact that magnetism and electricity are two, a right hand and left hand. They really are like sibling pairs. There's not much you can do with one without changing the other. So in this case, we had what is called an E3 component of the classic EMP. There are 3 components to an EMP. The first 2 are much faster acting. I think E1 component is nuclear, meaning like a nuclear detonation. The second one is, I believe, lightning. Lightning can cause, it's fast acting, it's just much shorter, much lower, more localized in its geographic location. And then there's an E3 component. The E3 component is caused by geomagnetic, disturbances. And a lot of people kind of yawn at the E3 component because it's slow. It's not nearly as quick as detonating an EMP device or a nuclear detonation. Nothing like that. It's much slower than that. But because it acts typically over minutes, not microseconds. But the problem with an E3 component is that it's over a insanely large geographic scale, right? Much larger than a nuclear explosion is even over. And so it is something that big industries, big power lines, big distribution lines, big communication networks, anything that's got tons and tons of cable over hundreds and hundreds of miles, they're the entities that worry about E3 components. None of the rest of us worry about them, because if we had a Carrington class event hit Earth just like the one in 1972 and it went over us, my phone would still work. I could still turn it on. no problem. My pacemaker would be fine. I could go start my car. Don't believe Michio Kaku, who says, oh, our cars would just freeze, our stoplights would turn off, everything would turn off. The E3 component of a big solar storm is not going to do that. Okay, but it does affect lines that are extremely long. Why? Because the effect is integrated. So you add this little bit plus this little bit plus this little bit. You do that for 1,000 miles. Oh my Lord, you got a lot, right? You got a lot of electric current, or at least electric potential that could then drive current. And that's exactly what happened to the Bell telephone system. Okay. Usually you guys are used to me talking about the power grids. Well, today, because I had to pick and choose, I decided to try a slightly different thing to show you that, yes, the power grids are affected, and we will talk about the power grids here in a minute. But that's not the only thing, okay? If you guys are old enough to remember what landlines used to be, does anybody remember the use of landline? Does anybody have a landline anymore? We used to be a nation and a world full of landlines. And we would communicate all sorts of stuff, multiple layers of voice and other types of private communications across these massive cables. One of the big systems was an L4 system. It ended up being replaced by, obviously, the L5 system. But back in August of 1972, it was one of the main systems that had a bunch of networks all over the place. And it got disrupted in literally 2 minutes of this CME hitting Earth, this ICME hitting Earth. And the reason for that is because of this massive change. We had, as a matter of fact, and this is just, I mean, there's other pictures, and I don't think I show the others. No. They had there was a really, really good, this analysis done by Anderson et al., Anderson and Lanzarote. I don't know Anderson, but I do know Lanzarote. This is actually a very, very astute analysis, and yes, these are all space physicists, so they definitely knew space weather and knew what they were doing. But they did this analysis because there was the Plano and what was it? Cascade, Plano to Cascade. So this was from Plano, Illinois to Cascade, Iowa, link of the L4 network. And the reason why this particular part of the network failed was because it was basically running not completely north-south, but mainly north-south, whereas a lot of these others were running east-west. It also happened to be just at the wrong place at the wrong time. And as they started doing some of the analysis, this plot here is basically the kind of the culmination. It's just showing the kind of like the end game. But they actually did these contour maps for a whole bunch of different times. And it was very funny reading the paper, looking at, they had like, I don't know, probably 12 different plots where they literally hand drew these contour maps, and just did a very, very unique, very, very good job and thorough job looking at how much the magnetic field changed over time. And today, the current version of this is actually at the Space Weather Prediction Center. You can actually look at models of how the magnetic field changes, the geospace magnetic field model changes over time as it's mapped on the United States, as a matter of fact. You can actually even see one that has it all over the world, but they have a close-up one of the way it changed over the or you know, how it's instantaneously changing over the northern hemisphere, basically. Northwestern, you know, the western side. And in this case, you're looking at contours, and I don't know if you can read this very well, but what they're talking about in this left side is they're talking about magnetic field, how much it's changing. At 200 nanotesla per minute. You can see the old annotation for nanotesla was actually gammas. We used to call them gammas back in the 70s and even 80s, I think, before we finally converted to nanotesla. You don't see gammas being talked about too much anymore. But don't let that confuse you. So this was over essentially 1 minute. Yeah, 2241 to 2242 UT. 200 gammas, 200 nanotesla per minute change. And you can see that's what the contours are. So each one of these lines is a 200 nanotesla different, okay? So we were in the center of this, we were seeing changes at 2200 nanotesla. That was the peak of this. So this was changing per minute. So this 2200 nanotesla change in 1 minute, right? Here is a 2000 nanotesla. Here's 1000 nanotesla, all the way down to all the way down to, what is this? 700? No, 200. 200 nanotesla per minute change. Where is this? Does that say Dallas? Guys, that's Dallas. 200 nanoteslas per minute change, clear down to Dallas. That's insane, okay? Here's the peak of it, 2000 nanotesla change. Where's the Plano Cascade in Iowa? I don't know, somewhere in here somewhere, right? There's Plano. Oh yeah, they have it labeled. Thank you. There's Plano. So not even where the peak of this is. It's down here at around what, 600? 800. Between 6 and 800 nanotesla per minute change. Okay? 1 minute. You have that much difference in magnetic field. Why? Because the CME slammed into the front of Earth and it compressed that magnetic field, and those people who know what L shells are, it caused those L shells to really come in, which really caused the field strength to jump up, that in 1 minute, even down at the Plano location, you had over 600, if not 800 nanotesla jump up in strength. What does that do? Well, if your wires are directed along the strength, along the field direction strength, you know, the field direction, along the magnetic field direction where you're going to get the most induction of current. Did I say that right? Maybe not. Let me be careful, because the magnetic field is changing so much. I don't want to say magnetic field direction. If your wires are along the line, the same direction that you're going to get the most electric field induction, meaning that the magnetic field changes such that it wants to push electrons or it wants to push current in this direction. If your lines are in the same, pointing the same way, you're going to induce that current very easily. And that's exactly what happened, because here in Plano, the field line, or the field lines, the L4 system lines were going basically like northeast, which is kind of in this direction. And it just, everything lined up perfectly where it tripped both the lines that were going in one direction. I mean, because you had alternating current, I believe, going on through here. And so if you had because the Earth's magnetic field is wiggling, so you're going to induce electric current this way, and then 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 this way. And so it's going back and forth along these lines. And there's two ways to trigger. There were two ways to trigger the line. I don't know if they were relays. I can't remember. And I have it in the paper, and I looked at it, and at the life of me, I can't remember if they were relays. There was some type of converter. That's what it is, converter. I knew I had it, converter. They had a converter that would, if you tripped over a certain voltage, so I think it was like something 350 volts or something like this, because you already have voltage going through it, right? So now you just have to up the voltage a little bit. Well, that's potential. Voltage is potential, the potential to move current. And so if you got an electric induction of 6.5 volts per kilometer that's going along the same potential as the voltage that's already in the line, then you will experience a high current shutdown. If you had 8.9 volts, so about almost 9 volts per kilometer, with the line going, with the induction going the opposite direction of the Earth potential, then the low current shutdown will cause. So one goes with and one opposes, but either way, if you have too much current flowing, or if you're retarding the current, retarding the voltage rather, so that it goes to a low voltage condition, either way it'll shut down. And both conditions were met. So the L4 system along that Plano leg died. And this was 242 kilometer stretch. This is what an EMP can do. Okay. And in this case, what are we talking about here? I forgot what this is. Oh, and this is the direction. This is, so you have the magnetic field, the horizontal component of the magnetic field. Here's basically defining 0, and then this is up to some degree, some angle. And so they're defining how quickly the angles were changing. And you can see change in angle. So from 0 to up. And so basically the magnetic field at that time was sweeping it up in this direction, and you can see by how much. So in the Plano area, it was, goodness, looks like positive 30 to 60 degrees. So it was sweeping like this in that 1 minute. So the magnetic field, which was changing dramatically, turning northward. And it aligned, it caused it to align just with the Plano stretch of this L4 system in 1 minute. Now, how does that happen? Well, we were talking about the magnetopause. We're talking about when you have the front end of that magnetic system of the Earth. We call that the magnetopause, okay? Now, looking at this diagram, this is looking down at Earth from the North Pole, and they were showing different latitudes, okay? So you can see 80 degrees, 60 degrees. They're showing concentric rings, trying to give you an idea of where the latitudes sat. And they're trying to show you where the Plano location was, right? It's not at the high latitude. It's not up at the North Pole or even at the South Pole, right? It's at low latitudes. Okay. And here's the thing. Notice Plano was on the day side, right? Remember, that's CME, if you recall. If here's the sun, right, coming this way. The CME, this is east from the sun's perspective. That's west from the sun's perspective. Where was that CME? East, right? If I go way back, no, that's it, right? When it hits Earth, where's the apex of this thing? Here's Earth. It's to the east of Earth. This is east. This is west. From the sun's perspective, that's east, okay? Because you're looking down at the sun from the North Pole, you're looking down at the Earth from the North Pole. So the bulk of the CME, this big massive thing, was hitting Earth to the east. Uh-oh. As this thing's moving through, right, it's moving to the east. So what happens is that you have a magnetopause, okay, and you have all these different spacecraft, right? You have ATS-5 in this case, ATS-5. We also have the Explorers, but here's Explorer 45, okay? So we have these spacecraft that are out here, and they're able to tell where that magnetopause is. Okay. For reference, here's geosynchronous orbit, okay? Geosynchronous orbit is typically well inside the magnetopause. This is where the magnetopause typically is during quiet conditions. Way out here, sitting at around 10 RE, 10 Earth radii sunward, right? Because the sun is blowing solar wind this way. Okay. This, which I probably should have drawn in later, is where the magnetopause, I just took the measurement that they did, right? If I take this off, right? They drew the magnetopause because they didn't have anything over here, so they couldn't tell, but I'm just going to draw it symmetrically. Looks reasonable, right? So you have a magnetopause that went from 10 to less than 5 in 1 minute. What does that? Oh, a fast CME. That's a bumper car. Can you imagine all that dayside flux that's here, right? All those magnetic, like we got the magnetic slinky. Okay, so in this case, we're looking down at the North Pole. So the magnetic slinky actually sits like this now. Okay, it's going around the Earth like this. Okay, we're not looking at it this way. We're looking at it this way. Okay, but nonetheless, you still have to crush this thing. You still have to crush it, right? You still have to push against it. So in this case, if I pull this way out here and see if I can make it work. So if Earth is in the middle, hello, you see the little plus in there? There he is. That's Earth. So now the slinky is sitting kind of like this. Let me make it this way. So now there's Earth again. See the plus? Okay. And now this shock is pushing the slinky this way. And these little loops of the slinky are collapsing, are getting smaller, okay, as I crush it in. And so what's happening is that it's strengthening everything, all that dayside flux. Probably strengthening the whole thing, actually, as the whole thing crushes in. And that rapid change from here to here really boosts that that magnetic field strength. And because it was boosted even more on this side, that was where the big impact was really leading the charge. That was going to be where the fastest, and I probably should have had this arrow here, now that I think about it, because that's where the CME was really slamming into. And look where Plano had happened to be, right in the wrong place, but not at high latitudes, right? Where you'd expect for a geomagnetic storm, that's where the magic happens, right? It always starts from the North Pole, and you've seen me wear the polar cap and kind of come down. Not this time. This is much more equatorward. This is why people at low latitudes worry about the E3 component and worry about EMP. They worry about space weather too, but for a different reason. EMP is much, much bigger at lower latitudes. Why? Because the magnetic field strength of the Earth is bigger anyway. So the bigger the field strength is, the bigger the chance it has to induce currents. This is why everybody who says, oh, the weakening magnetic field, it's going to ruin us all, and Tamitha is just silly because she doesn't understand that a weakening magnetic field makes these CMEs hit harder. Really? Really? Because if we're worried about power grids going down and we're worried about EMPs, you got to have a strong magnetic field to generate a strong EMP and a strong induced currents, induced voltage, induced anything into the ground or into the lines. Okay? The weaker stuff is up at the poles. And guess what? That's not where you get strong GICs. That's where you get strong auroras. That's where you get strong geomagnetic stuff going, just because you've got a field that's moving around and wiggling a lot more up there during a big geomagnetic storm. But the stuff that you worry about is when you have the stronger magnetic fields. Okay? The stronger magnetic fields are either stronger magnetic fields because you've got a strong Earth magnetic field and it's being compressed, or you're at low latitudes. But it's the strong magnetic fields that end up inducing the largest currents in the ground, and therefore has the largest impact on the power grids. What does a weakening Earth magnetic field do? It makes us go, whew, wow, we get a breather for a little while. That's great. You know, I can't wait for that. Now, is it going to cause problems for particle precipitation and other aspects of space weather? Sure, because space weather is always a mixed bag. But anybody who tells me that I'm not taking a weakening Earth's magnetic field, not taking it seriously, really doesn't understand space weather and really what the big extreme events are capable of doing. A weakening magnetic field in many ways, when it comes to big transformers on the ground, which is the ones that will send us to the dark ages if they ever break down all at once, it's the weakening magnetic field that gives us a better chance of surviving them. Okay? I do know what I'm talking about. You can see it right here. So the interesting thing in the summary is that, and I remember, what do I want to say? Did I want to just read this? I can't remember if I wanted to read this. It says the geomagnetic field, or the geomagnetic disturbances, were produced primarily by large distortions of the Earth's magnetosphere, whose boundary was observed to be pushed inward to an altitude of about 4 to 5 Earth radii over North America at the time of the L4 outage. Therefore, the geomagnetic disturbances that produced the outage did not arise from enhanced auroral current systems that are normally associated with power system problems during magnetic storms. See that? It wasn't the aurora. It wasn't a big geomagnetic storm. You didn't need one. This thing was so fast, it was a bumper car. Bagoong! And that was enough to create that EMP and take out the L4 lines. So does a Carrington class event need to be aurora from on high? Does it need to have those pictures of basically buildings on fire and all that crazy stuff going off in the sky? No, it doesn't. It can be something entirely different. But look what had to conspire for that to happen. Not only did you have to have the fastest event in the world, fastest event ever on record, But look at the power line. Look at where the lines, the L4 lines, they had to be angled a certain way. It had to be in the right place at the right time. The CME had to be in the right place at the right time. Did you get it? There's lots of things that must line up in a row for a Carrington class event to do the kinds of damage that certain events are capable of doing. There is a lot more potential in Carrington class events that will ever be realized. And in this case, this one had a massive potential to cause a geomagnetic storm, but the fields weren't aligned the right way. That's why we didn't get one. What we got instead was a bumper car. Now, what type of problems did it cause? In under 5 minutes, because of this bumper car, we saw huge voltage swings in the northern tier of the USA. We just saw the reason why, right? We just saw in the northern tier of the USA this nightmare. Now we know why. This isn't Aurora. Not even close. There was the outage. This is a summary of the outage. It induced an electric field of an average of 7 volts per kilometer, which exceeded the high current shutdown. You saw the more details from the paper. Coincident with fluctuations of about 800 nanotesla per minute at that 2-minute time, really 1-minute time. In northern Canada, d by dt, that's the change of magnetic field over time. Sorry, I'm borrowing this from Dolores Knipp. She let me have her charts a long time ago. It was really sweet of her. And so I've left this for her, but this is made more a little bit for a scientific audience. So dB by dt is really the change of the magnetic field over time. It was over 2,000 nanotesla per minute. Well, we saw that, right? We saw that just in that paper from Anderson and Lanzarote et al. The Manitoba Hydro Company recorded 120 megawatts drops in their power supply supplied to customers. Here's all the issues. These are having power to system disturbances, or SICs. SIC. Sudden, can't be. Not sudden storm commit, sudden, don't know. Can't remember, SIC. Sudden impulsive currents, I can't remember, something like that. But it's what we were talking about, the induction of the currents. So you can see where the strong, moderate, and weak areas, but lots in Canada. And remember, that was kind of where the peak was, remember? If we go back to the northern tier of the United States, and in Canada, look where the peak was. A little bit moved to the west in this case. But if you watched the whole progression of things, you saw it just really just racked this whole area. I just can't show them all. Additional long-lasting effects. Whoops, I'll stand over here. In Newfoundland, geomagnetically induced currents were activated. They activated protective relays numerous times through both August 4th and 5th. If you remember, we had, when we looked at the solar wind data, it was solar wind data, but it was the speed from Prognos. You saw that it took 2 days until the 6th before the speed dropped below 800 kilometers a second, which is faster than really any CME we saw in solar cycle 24. I mean, tells you how fast this thing was. And that's maybe not a fair comparison because cycle 24 was a snooze-worthy cycle. It was one of the weakest cycles we've seen in ages, right? Even this cycle, as active as it is, yay, it's active, it's more active than we've had. It's still pretty yawn-worthy. It's only about average. We haven't seen any big cycles for quite some time. Okay, anyway. There's also strong GIC effects in Ohio and Maryland. And see, here I am talking about Carrington class events, and I feel completely comfortable saying, yeah, this cycle's reasonably yawn-worthy. We haven't had any really strong cycles. And I can actually look at that and say, and be excited that, we might see bigger storms in the future. And there's a reason for that. It's not because I want us to go to the dark ages. It's not that at all. It's just that I have the understanding, and hopefully I'm beginning to impart that same understanding in you, that there are so many factors that, and so many ducks in a sense, that you have to line up in a row that all have to just absolutely be right at the right place at the right time with the right conditions, and all of it has to work in order for something catastrophic to happen. It doesn't just happen as soon as the sun launches a Carrington class event. It doesn't. That's why when I see a huge, big, fast event, I don't immediately go into panic mode, even if it's directed towards Earth. I don't. Because it's like, well, we have to kind of see what it is. What is this thing? Okay, yeah, it's fast. Maybe it'll be a bumper car. Maybe we have to worry about EMP, right? But maybe it'll graze us. Maybe it'll be deflected. Maybe, you know, there's going to be a lot of traffic in the way and that'll slow it down. Maybe it'll just not even have the right magnetic field. Oh, well. And I'm sure not going to worry about any spacecraft that's going to encounter it out there in interplanetary space, because it's really the Earth's system that causes problems. It's not interplanetary space. If anything, you want those spacecraft to be out of the Earth's system. I mean, I actually, in many cases, I'm actually appreciative if when the magnetosphere comes in as far as this, because then it gives some of the spacecraft some breathing room for a period of time as they go out into interplanetary space. They can, you know, at least in the magnetopause area, they're not quite as inundated because the magnetic field strength drops. Okay, so what else does it do? Yeah, I'm going to get into the part that really is what finally put this thing on the map. So just because the Bell telephone system dropped in a certain area, that's not a big enough thing. Just because we had power outages, that's not a big enough thing to make it like stand out, right? Otherwise, we would have heard about the 1972 event far sooner than we did. But it really took Dolores Knipp's paper to really bring to light some very interesting things that we had not known before. Now, Dolores has an esteemed history in being both a meteorologist, a space weather physicist, and has spent time with the military. And so she has a vested, you know, she's interested, right? Vested interest or just a personal interest in how space weather may affect military. And so she did some digging in the archives and found when they had declassified some reports from the Vietnam War. I think she said that they declassified them back in 2016 or something like that. And so she immediately started diving into some of that stuff because there was just some fascinating information. And when she came across what happened in 1972, I don't remember if she said she started digging to see whether or not it was a space weather event, or if she had known about the 72 event and then looked specifically for military, you know, disasters at that time. I don't know, it was chicken and the egg kind of thing. I don't know which came before. But however she stumbled upon it, we were forever grateful because it ends up being a really interesting tale. So we had, as the United States, we had minefields back in Vietnam. And the Haiphong minefield, I'm probably just butchering the name of it, was the one that ended up being very susceptible because of the type of mines that we chose to employ. We had something called destructor mines, and for those of you who are familiar with them, or not familiar with them rather, these DSTs, they were designed so that they would have magnetic relays that would trigger in case any big change in the magnetic field occurred. And these, what would happen is that you would get, what should I say? Anytime you'd have, and the reason for them was that if you had a big metal hull of a ship, this was the idea, that if you had a big metal hull of the ship, well, it will, just having a metal hull, it alters the magnetic field, the local magnetic field nearby. And because it can alter the magnetic field, that as it drives by a mine, the mine will sense the altering magnetic field. It'll sense a pristine field, and then the ship enters view, and it changes the magnetic field, and it continues to change, and then it changes it differently as it drives by, and then it eventually moves back out of the way, and you'd have a pristine magnetic field again. So there's a nice change in the magnetic field rotation and even possibly strength, depending upon the size of the hull and the proximity of that metal hull as it goes by that mine. And if it's big enough, right, and strong enough, change, it will say, ah, there's a ship nearby, boom, and it detonates. That's the whole point of it. Well, nobody back then, as we talked about before, we didn't really understand coronal mass ejections. We hardly understood that there was a solar wind. We sure didn't know how it worked. And that's on a scientific level. And therefore, do you think the military had any clue? No. So when they designed their mines, they didn't design it with space weather savviness in mind. And you just saw what that bumper car did, right? You saw 2,200, was it 2,000 or 2,200 nanotesla changes over a very short period. Well, what ended up happening is that this bumper car ended up changing that magnetic field so strongly, even where Vietnam was, that it caused almost basically the entire fleet of DSTs to detonate. And according to Gonzalez, it says during the first few weeks of August, a series of extremely strong solar flares caused a fluctuation of magnetic fields in and around Southeast Asia. The resulting chain of events caused the premature detonation of over 4,000 magnetically sensitive DSTs, which are destructors, which were over half of the DSTs planted over the past several years. Can you see why this was classified? The military went nuts, right? What kind of technology is this? Who could possibly be doing this? How in the world did all of these just detonate all at once? This was classified for a very long time, right? 2016, from 1972 to 2016, right? But it turned out, as they did their reports, and you can see here's the minefield. Here you can see all the areas that were impacted, all across North Vietnam. Right, so a huge area. And there's the declassified document that was filed in 1976 and declassified, I think, like I said, in 2016 that Dolores looked at. And the discussion is that they had been deployed during Operation Pocket Monkey. I have no idea why they chose that name, but this is Operation Pocket Monkey. And it was a mining campaign in 1972 against the North Vietnamese ports. But here's the funny thing, is that some of the detonations were actually witnessed. On August 4th, 1972, the crew of the U.S. Task Force 77 aircraft flying near a naval minefield off the waters of Han La observed 20 to 25 explosions over about 30 seconds. They also witnessed an additional 25 to 30 mud spots in the waters nearby. So they watched this, and could you imagine? I mean, this is a mine. This is an example of a mine detonation, but this wasn't what they witnessed, right? Because there was no ship going by. So imagine this without the ship or without the boat going by, and the detonation occurs, and they're just seeing them pop, 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 right? And then they're seeing other ones that it's just mud kind of coming up. So you know ones that were lower in the ocean or somewhere else were also going off. Very frightening, I can imagine. So here was some interesting, just some anecdotal stuff. Interesting that military brass went into the Space Weather Prediction Center. Back then it was a Space Environment Center. It's known as the SEC, I believe, back then. And it says, those conducting the investigation into the mine incident visited the Space Environment, it was called the Space Environment Laboratory, that's right. It was a Space Environment Laboratory, then it went to the Space Environment Center, and now it's known as the Space Weather Prediction Center. That's how it tells you how many iterations have been going on. So the Space Environment Laboratory, which was really not set up much prior to this, maybe 20, not even 20 years prior to this, I think. One of the scientists at NOAA at the time, Brian Fraser from Australia's Newcastle University, he remembered, and he actually got interviewed by it. And I can't remember who did this interview. It says, I was on my first sabbatical leave at NOAA working with Wally Campbell, Wally Campbell's group, which even I have a couple colleagues who worked with Wally Campbell. And one day, in Wally's office, I noticed a group of U.S. Navy brass hat gentlemen and a couple of dark suits. The dark suits, those are people you don't shake hands with. Those are people that if you try to introduce yourself to them, they just look at you like, because they're not allowed. They're not allowed to say who they are or where they're from. And I know that quite well from my years at Aerospace. Brian said he had later quizzed Wally on what was going on, and Wally explained that they were concerned about geomagnetic field changes triggering sea mines laid in Haiphong, North Vietnam. And there was no mention of whether or not they had exploded, but maybe Wally was being coy. And of course, it was all probably top secret back then. So it says the outcome of the investigation is stated in the declassified Navy report, detailed the high degree of probability that the destructor mines had been detonated by the August solar storm activity. In the report, it said, as the result of the extensive analytical effort, the Navy Ordnance Systems Command on the 5th of September advised the Sinopac fleet and all others concerned that there was a high degree of probability that the sensitive and some insensitive DSTs seated in North Vietnam waters had been detonated by the solar storm activity in early August. The September storm activity, as it turned out, did not have sufficient magnetic activity in the frequency range needed to fire the DSTs to have any effect on the minefields. You know what that means? The September event as it turned out, didn't have sufficient magnetic activity in the frequency range required. Short. That means short time range, meaning it didn't have an EMP. There was significant magnetic activity, but it was just a normal geomagnetic storm. It wasn't the EMP. They didn't understand all that back then. So they were scratching their heads going, why did this one but not this one? They didn't get it. Took them a while to figure it out. Okay, I think before I jump into the next bit, we'll pause for a moment. What do you guys think about this? Oh, I'm seeing laughter. This is good. I like that. It's a Carrington class event story and people are laughing. This is good. You're not scared. This is great. Oh gosh, because of Wally. Yeah, gee, Wally, why did those mines detonate? That's cute. I should have thought about that. Leave it to Beaver, right? Very cute. I don't know why you were so hard on the, yeah, okay. I know the joke. I know the joke. So any questions on this thus far? Let's see, I'm reading. Interesting, okay, thanks, very good. You guys are talking about tarot cards. Okay, Smash asks, Tamitha, why, any idea why many CMEs are not accompanied by Forbush minima? Some geomagnetic storms are accompanied by an uptick in cosmic ray flux. We have to be careful with the uptick in cosmic ray flux. It depends upon what's also happening. If there's a radiation storm happening, then that can mask things. If the Forbush decrease is minimal, typically because there's not a shock involved, the CME is moving very slowly, and the CME may be very weak. If the CME basically has only the field strength of the solar wind, the Forbush decreases are very mild. And it also depends upon which station you're looking at. Remember how I showed with Japan how different, how incredibly different the Forbush decreases can look, and even the GLEs can look, depending upon where you're located. So South Pole has a different view than lower latitudes. And so and that has to do with rigidity of particles. So you have to kind of understand a bit, understand that that not every station is going to show a Forbush decrease. A lot of times they do. Higher latitudes have a better tendency to show Forbush decreases in general, but that's not always true. And again, it also depends upon what their asymptotic viewing cones are. Most of the time it's an omnidirectional thing, but I have seen times where a station that you would think would be showing a Forbush decrease, but then if you look at its viewing cone, it's like behind Earth, deep in the Earth's magnetic tail, and okay, it's not seeing it. And you can kind of go from there. But cosmic ray neutron monitor data it's tricky. It's not something I advise those who are not well versed in cosmic ray analyses to pick up. I myself will not do a formal cosmic ray analysis without help from people like the retired John Bieber and Paul Evenson and others who are from Bartol, let's say, the Bartol Institute. There are very savvy scientists out there who can use neutron monitor data in a very quantitative manner, but it is non-trivial to get there. So that's the best answer I can give you, being someone who knows enough to be dangerous. I don't pretend to know all the answers, so I may have left out one or two of the answers to that, but hopefully that gives you enough to go on. This is SP. How many AUs in the distance in the sun's heliosphere? How far does the heliosphere go out to? Oh, good night. I forget. Quite a few. Hundreds. 100 more? Anybody know that off the top of their head? I'd have to, at the top of my head, I'd have to Google it. I don't play out at the outer reaches where our heliosphere, the termination shock and all that ends. Anybody remember with the Voyagers going out where the termination shock was? How many AU out that was? A quick look at Voyager, looking at the Voyager data and when they saw the termination shock will give us a good idea of how far out. But it's quite a bit. 80 maybe, if I'm trying to remember. Say 80 to 100 is my guess. But I may be completely wrong. It's not an order of magnitude more or less, I don't think, though. Okay, good, Smash. I'm glad you like the answer. So the Earth's magnetic field is strong and we get a direct hit by a strong CME, we're in trouble. No, not necessarily. A strong CME, what do you mean by a strong CME? We've been hit by strong CMEs and they have the field orientation the wrong way. They end up being a bumper car. So it causes problems, or it could cause problems, but it may not cause the problems that you expect. It all depends. It all depends upon so many things. Okay. Let's see. Secret Owl, I don't know if that question is for me. It looks like you guys are talking amongst yourself, which is wonderful. Oh, is it like 200 AU? Is it that far? I didn't realize it was quite that far. I thought it was in the 80 to 100, but I'm easily wrong. Like I said, that's not an area. I don't look at the outer heliosphere very much. I'll teach it, but by then I have charts that remind me where things are. I have known and I've forgotten it 1,000 times because right now I'm trying to fill my head with Carrington class event stuff, so I have to push other stuff out to put the new stuff in. my brain's only so big. Okay, let's see. Yeah. How far out is it? 113? Ah, according to Wiki, 113. That sounds more reasonable. Yeah. And 93. See, those are more reasonable. I said anywhere between 80 and 100, so 113, 93, somewhere in there, 113. And realize, 120, good, 113, great. So realize too, when I taught there's a class series called, I think, the H series. That's the breathing heliosphere series. That 113, 93, 80, whatever, those numbers are going to change depending upon if we're at solar maximum, where the heliosphere is as strong as it's going to be, or I got to be careful. That may not be, I got to be careful because solar wind, I would think its solar max would be when the heliosphere is as big as it's going to be, but that's not when we have the most coronal holes in the fast solar wind. Our solar wind on average during solar maximum is actually diminished somewhat. So how much does that count toward pushing out everything? I would still think, because it's a pressure balance and not just a speed thing, I would still think solar max is likely when our heliosphere is the furthest out. And then as minimum, as minimum takes hold and our sun becomes more dim, even though we have some fast solar wind at times, I think overall the solar wind strength, meaning the density and the temperature and everything that then combines thermodynamically to create an expansion of our heliosphere, you know, an adiabatic expansion of our heliosphere, I would think that that overall would be less. So the pressure balance would be at closer to the sun during solar minimum than during solar max. Now, I could be wrong, but because it's not just about speed, it's not just about solar wind speed, it's about lots of things. And it might even be the declining phase where we actually, instead of at solar max, peak, because our dipole field will then have been reformed. But that's just me, you know, putzing about in my head, thinking about all the complementary physics that goes on and the mechanisms that would contribute to a pressure balance and where that would be. But that termination, that edge of our heliosphere, it is not stagnant. It does breathe in and out, okay, as the activity of our star changes. So just be aware, it's a squishy number. But yeah, anywhere 93, 113, all those numbers sound good. Okay, let's see. Yeah, Shibi, feel free. Like I said at the beginning of this, these are long, these are always long topics, so feel free to step out and catch up later. Thank you for joining us for as long as you have. Yeah, we ultimately don't know what solar wind is like at the solar poles during solar minimum. It's fast, and we do kinda, because it's during solar minimum is when we have those coronal holes that are really well formed. So very fast solar wind at the north and south poles, and it's very pristine, right? That's when the solar minimum is when we have the best idea of what our solar dynamo is and what it looks like, the magnetic field configuration of the entire sun looks like, because it is so well behaved. We have a beautiful magnetic field. Dipole field is the one that's taking over, and there's not a lot of activity going on, not a lot of sunspots to kind of muck up the mix. And everything is, it may not be at the potential field state, but it's pretty close, meaning that there's not a lot of energy or not a lot of forces on the sun's general magnetic field. And so they look very much like the models that we can put out, because we create potential field models, which means any current flowing is flowing the direction of the magnetic field, and therefore it's not causing the magnetic field to bend or stretch. That's the way that the magnetic field likes to relax. It likes to have potential field so that it's not moving. Otherwise it would be shifting. It wouldn't be in equilibrium. So when is solar minimum coming? Not for a while, probably about 7 years from now, maybe 8. Okay. Any other questions? Let's see. I see lots of conversation. This is great, guys. Boy, for being in the habitable zone, this is Mark Nokowski. Boy, for being in the habitable zone, we've been pretty lucky all these thousands of years so far. Well, yes and no. I mean, I think we don't give our Earth's magnetic system enough credit. I mean, it's really designed, you know, almost as if by design, right? For those of you who are God-fearing, almost as if it's been designed to keep us safe, right? And it's very forgiving and very robust and very regenerative. And as long as our solar dynamo, or I mean our Earth's dynamo continues to generate, which will be for quite some time yet, we're going to be in good shape. And all the uh-oh, Cheyenne, uh-oh, gosh. Hope not. All the interesting things, you know, as we talk about the magnetic field flipping, another reason why I'm kind of cautious when it comes to talking about the Earth's magnetic field flip is that the more I've dug into it, I mean, it's going to be a fascinating time when the Earth's dipole field component flips, right? And the radiation belts get all messed up and possibly just go away, period. And everything changes, and the way we understand near-Earth space is going to change. And it's going to be just as crazy out in near-Earth space as it is going to be on the ground for us trying to use compasses. We can't use them the way we used to. So we'll have to figure out new ways of dealing with all that. But and remember, that's going to be transient. But the reason why I don't go too far down that rabbit hole is because the more I've talked with geophysicists and the more I've read papers on our weakening magnetic field, the more it becomes obvious that even the geophysicists aren't willing to say, yes, the field is flipping. Why? Because in the geological record, we've had dips like this in the past, and then the field comes back. And it's like, what was that? You know? It's like a little burp in the timeline. I don't know. So is there a chance? We've had even deeper dips than this and then a recovery with no flip. So I'm not ruling, if the geophysicists themselves are not willing to commit to the idea that our Earth is actually, the Earth's dipole field is actually flipping completely, then why should I? It's not my field of expertise. So is it possible that the Earth's field is flipping? Well, absolutely. Is it also possible that it's just a dip and then a recovery? Yes, that's possible as well. So until we get to the point where geophysicists say, oh yes, we're past that point of no return, we are definitely on the way to a geological flip in the dipole field, I'm just kind of sit here and go, okay, you know, and talk about it from the perspective that I know regarding these big storms and how big CMEs interact with our Earth's magnetic field, and in all the ways other than the particulate radiation, in all the ways that really matter, because the field, even as the field weakens to the point where you're getting deeper penetration, and you could possibly have more pickup ions being taken off of our atmosphere, it's not going to last long enough for it to be a problem. We have, you know, a little bit more of the oceans are going to evaporate. Are we going to even measure it? I don't know. Probably not. I mean, it's kind of, we've had it happen before, and we've not seen appreciable or any appreciable loss of ocean. Only when the dynamo dies completely will then the oceans begin to bleed off into the atmosphere, and the atmosphere be stripped off by the solar wind, and then we'll be like Mars, right? Mars is our future, but Mars is not our future simply because our magnetic pole is flipping. Mars will be our future, our distant future, when our Earth's magnetic dynamo dies, and that's not going to happen for quite some time. Definitely not in our lifetimes, so, or our grandchildren's lifetimes, or our grandchildren's grandchildren's lifetimes. It's a long way away from dying. So, you know, that's why I don't worry about it as much as people say, well, you should be worrying about it more. No, I'm not going to. Okay. Wow, that's a neat piece of trivia. If Jupiter's magnetosphere were visible with the naked eye, it would be the size of the full moon. I can neither confirm nor deny that, because, and I don't mean that from a I plead the fifth point of view. I mean, it sounds plausible. I know the Jovian system is pretty big. What's even more fascinating is that it rotates. The Jovian system rotates. The Jupiter rotates in 10 hours. I mean, so the thing is just rotating like crazy, wobble, 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 and it's really interesting how it interacts with the Sun's system. Just another piece of trivia: the types of CMEs that cause geomagnetic storms at Earth don't work on Jupiter. Jupiter's field is reversed compared to ours, so Jupiter needs CMEs that have northward pointing field, not southward. Isn't that funny? To cause a big storm there. But anyway, it's another piece of trivia. But it'd be interesting to look at and draw the Jovian system next to the moon. I might look that up and see if anybody's done that. That's pretty neat. Thanks, Smash. I appreciate that. Okay. What effect would a polar flip have on earthquakes here in California? You know, here's the funny thing about earthquakes. And again, I am not someone who's going to as many of my mainstream colleagues do, they shut down anybody who talks about earthquakes and says there's no relationship. I won't go so far as that, because I know that when we don't know or don't see correlations in data, that doesn't mean the correlation doesn't exist. It just means that we can't see it because of maybe something hasn't been subtracted off. We haven't understood enough of what primary drivers exist. So it's kind of like, as I've talked about it before, is like a baby in a bath, you know, baby toys in a bathwater, right? My child was young when I first came up with this analogy, and I've just kept it. You have soapy water in a bathtub, and there's a bunch of toys down at the bottom, and you can't tell the toys are in there until you drain the bathtub, right? Well, the primary drivers of earthquakes, which is the geophysical, you know, plate tectonics and all of that, those geophysical drivers are the main drivers of earthquakes. There is no doubt, right? And until we are able to subtract off the effects of that and see what's left over, what the residuals are, what's still there, that's when we'll see the toys in the bottom of the tub, right? That's when we'll be able to see whether or not space weather plays a role. Now, are there mechanisms, plausible mechanisms? Yeah, you know, GICs, for example, you're changing, you're causing forces and you're changing potentials in the rock. Could that potentially have things like piezoelectric effects and stresses? Sure, could. But it's so far down in the noise right now, we can't see that correlation if it exists. So how will the weakening field of Earth affect that in terms of earthquakes, not just in California, but anywhere else? Well, probably it'd lessen the effect, right? Because you're inducing currents and stuff in the ground, which are mechanisms by which you could see this kind of thing happening. It will actually lessen the effects. So anything that's inducing currents into the ground, right, and anything that affects, like L4 cables, right, like big power grids, like potentially earthquakes, it's going to lessen the effect. Okay. We're getting a reprieve, guys. Do you get it? It's not the doom and gloom you want it to be. I mean, I say that seriously, that you want it to be, because there's a lot of people out there who absolutely want it to be doom and gloom. I don't agree. I don't agree. I'm not taking it lightly. I'm looking at the physics behind it. Okay. And for those of you who are, who really are fringe scientists and want to try to find correlations when it comes to earthquakes, hey, here's a great ansatz. Here's a great idea. How about taking Carrington class events, right? The biggest of the biggest, and look for massive, like the biggest of the biggest earthquakes. Do they correlate with Carrington class events? If they don't, if they do, hey, bring it up, write up a paper, get people to talk about it, because it'd be fantastic if space weather scientists could actually add that to the list of things that they do that make space weather relevant to society. That'd be great. So if you find a correlation, let me know. As a matter of fact, write a paper, present it at a conference, wake scientists up to that. But if you don't find a correlation, well, that means we just have to keep digging to see if there is one at all. It's going to be hard, and you're not going to get mainstream science to take it up anytime soon. It's definitely a realm of fringe science, so keep working at it. And eventually, if the truth is there, that's the neat thing, is that if there is truth, it will always be found. It just takes time, right? And it takes the advancement of science. So, okay, I think, is that a good enough break? Everybody stretch their legs and get ready for the next bit of this. I think I've got pretty much everybody's commentary. Would I like to comment on how unlike the solar system, the galaxy, how unlike the solar system the galaxy is? The galactic core, is the galactic core dangerous to Earth? Well, it's too far out of the sphere. I'm not going to go into all of that right now. I'd like to focus on Carrington class events and some of the gravity waves and gamma ray bursts and stuff like that. I mean, you talk about Carrington class events. They're the ones that actually wreak havoc at Earth are already a rare occurrence. You go into things like gamma rays taking out the planet. I mean, come on, how many billions of lifetimes do you have to live before you see one of those? Obviously, you're not going to live to tell about it, but I mean, why do that to yourself? Is the universe filled with things that could absolutely kill us? Sure it is. But we're still here. And the reason why is because these things are so unbelievably rare that they're the things that scientists, that astrophysicists love to talk about. And they don't understand that when they talk about them in the, ooh, isn't this cool kind of mode, that they're communicating doom and gloom, and the average citizen, it stops their heart, because they think now they got to look up at the sky and worry which one of these little blinking lights is going to take them out next week. Like they're all snipers in the sky, all with their guns aimed at Earth. And scientists just don't necessarily appreciate that. And that's a real problem for me, because it's not fair. It's just not fair. Can't do that to people. Oh, speaking of, let's talk about some fun here for a sec. I'm going to plug in this cute little device that allows me to play some stuff. So here's some fun. Let's go back to communication for a little bit, skywave communication and stuff. Because what I'd like to show you is some interesting things that was going on in the atmosphere during this event, this set of events, right? So what I've got, I came across this and I thought, how cute. VLF emissions and whistlers observed in Japan for the 1972 events. Now remember, Japan, low latitudes, right? During all of this stuff. So here we are in the heart of the Earth's magnetic system. Magnetic field strength is really, really high. The L shells are being crushed in, so it's really strong magnetic field, all very densely packed and everything. And what a perfect time to really kind of have this be a megaphone for all of the fundamental processes that are going on in the near-Earth system. So when a big event like this hits Earth, you know, we talk about even when a big Carrington class event launches from the sun, we talk about the sun screaming, right? That's one of the things I've mentioned many times with these big radio bursts. They cause radio blackouts because the sun is making so much noise as it's screaming out and launching these things. We don't necessarily appreciate the fact that when these things hit Earth, now it's the Earth's turn to scream. And it does. It screams. It screams at a much lower frequency because its voice is really tiny, tiny. So it doesn't have the ability to scream at really high frequencies, but it does scream. And it screams in things in different types of radio noise. Chorus waves, whistlers, hiss, plasmaspheric hiss. There's all sorts of really cool ways of screaming. And during this particular event, I found out that in Japan, they actually looked at the anomalously high incidence of both whistler waves and chorus, or not chorus, but hiss, plasmaspheric hiss, and I thought it was fascinating. So I'm going to show you. This was done by what is it? Ondo from the Radio Research Laboratories in Tokyo, and Tanaka. I know Tanaka's work. I don't know Ondo's work, but Tanaka is a name I cut my teeth on some of these papers. And so this was really cool, 1972. So what we're looking at here is a timeline from August 4th essentially through the 13th and beyond. And on this side, this is the whistler rate. Okay, I think does that say rate? Yeah, average number per minute. Okay, so how many whistlers are they hearing per minute? Now anybody who doesn't know, maybe I should do this first. You want to know, let me play what a whistler sounds like, okay? Hopefully you can hear this. Let me just play it and see. Wait, let me make sure that my speakers are the right speakers. USB codec. I think they should. Hopefully you'll hear this. You hearing? Is anyone hearing this? You should be hearing it. Let me turn this up. Oh wait, I know what. I think I got to do this. Hold on one second. You might lose my vocal for a second while I turn this into tape and add to main mix. Let's see. Let's try again. Now, I don't know if you can hear me. Yeah, you should be able to hear me too. Did you guys hear that? I could turn it again, make it louder. Space whales. I love it. That's awesome. Space whales. Yeah. Right? So these are things that, because I can't hear it, I could only see that it was on my meters, I could see that it was showing. So these are whistler waves. And I've talked about them in the past, but I'll talk a little bit about them again. What they are is essentially lightning, okay, the sound of lightning. And you're hearing lightning from, if you're hearing them on a wire, someone said that you heard it on a what was it, when you were a kid? This is the original OSOK. When I was a kid, there was a phone number you could call it, and it sounded like that. Yeah, you might have actually been hearing whistlers on that, because you actually get those electromagnetic interferences. And what it is that if you have the Earth, right, sitting in this the heart of the Earth's magnetic system, the magnetic field lines, which are each one of these little, slinky things, right? That's a magnetic field line that goes from the northern pole or northern hemisphere to the southern hemisphere. And not all the magnetic field lines go straight up at the pole. Some of them are connected a little bit lower, at lower latitudes. And as a matter of fact, the closer they are to Earth, the lower the latitude they're connected. And I've talked about this in the M series. You'll learn that they're all what we call L shells. So when at low L shells, meaning really close to the Earth, and remember, this CME squished everything close. So there were a lot of L shells of really high magnetic field strength and at low L. And so what happened is that lightning from the southern hemisphere, essentially, if you're in the northern hemisphere, if you're in Japan, as it is in this case, you were hearing at what's called the conjugate point in the southern hemisphere, meaning basically the same magnetic latitude and longitude. In the southern hemisphere, you'd hear lightning strike, and a wave would shoot up that electromagnetic wave would shoot up that magnetic field line and wiggle the field line and then enter into the northern hemisphere. And because of the fact that it's such a long distance, you would get this dispersion, what we call dispersion. And it's a frequency dispersion. The higher frequencies were faster. It's like thinking of being in a foot race, right? Faster runners, you all start at the same time, but by the end of a long distance race, the fast runners are spread way out in the field and the slow runners are way back, right? That's dispersion, believe it or not, same kind of thing. In this case, we're not runners, we're frequencies. So the high frequencies were the fast runners and the low frequencies were the slow runners. So by the time it went from the southern hemisphere all the way to the northern hemisphere, the high frequencies were way out in front and the low frequencies were, the puffers in the back just trying to get to the finish line, right? And so when you heard them in the northern hemisphere, you'd hear these high frequency tones and they'd slowly descend as the lower frequency tones caught up and finished the race. So that's what gives the whistlers the characteristic sound. But the thing is, whistlers are long, right? The whole thing for it to go from start to finish is a couple seconds or so, right? Look at the occurrence rate. This is 10, 20, 30, 40, 50. At the back part of the storm, because the storm started late on the 4th, right, almost into the 5th. So that was like right here is when the storm really, that bumper car hit, okay? And then it did storm a little bit, but that bumper car was still pushing against the Earth. Remember, it took until the 6th for it finally to the solar wind to slow down enough that it wasn't just slamming into into the Earth's magnetic system and squishing that field up. So, and remember, we weren't eroding the flux either. So it's not like you could blow the bangs back of the hair and have it all go back to the tail, because the geomagnetic storm really wasn't that big. The field wasn't oriented in the right way to make that happen. So it was really just a bunch of crushing of this, everybody crowded into a tight room because of this fast solar wind. So for these 2 days, you had not really super strong storming, but you sure had a lot of crushing of the magnetic field close to Earth. So it really it was like a megaphone for these near-Earth radio, phenomena to be just not amplified, but yeah, well, in a sense, maybe amplified, but definitely allowed a lot more of it to occur and be recorded, at least, to be heard. And so the frequency, the amount of times they caught whistlers, this is 50 times, right? By the time you got to August 6th, 50 times per minute. Is that 50? God, 50. Over 50 times a minute. These things last several seconds each. So if you're having 50 plus of them over a minute, that means it never stops. You're hearing, right? Because they each last more than a second. They last 2 or 3, sometimes 4 seconds long before the thing's over. And if you're hearing 50 of them a minute, there's only 60 seconds in a minute. How many of these are you hearing? Isn't that insane? Could you imagine trying to get on, your telephone or you know, the radio bands or anything else, and you're just constantly hearing just sounds like thinking like it's Star Wars, and there's, you know, or lightsabers or something being fought. I just thought that was fascinating, that this was going on, and that these guys had an ability to record it. So, you know, you're going to hear. So from this perspective, not only are you going to hear a solar flare, which is this is what a solar flare sounds like on the amateur radio bands. Listen for it. I'll play it for you. Okay. This is the sun screaming.
Hopefully everybody will be in there. Have a good day. 73 KF7RET.
Yeah, what happened to the band? Is I weak now too? Yeah, we got a solar flare or something. 73, Rick, if you can hear me, you tell us CQX.
Right, so from this perspective, this is just static. Hopefully you guys heard all that. And the guys are saying, oh, I think we have a solar flare or something, because they couldn't talk. They're like 73, and they're just getting out of Dodge because there was no way they could actually hear each other anymore. So that's the sun screaming, right, when you're doing amateur radio. So not only you have to deal with that kind of stuff going on, but then you have to hear the whistlers, right, so that you have that laying on top. And then also you get this stuff. This is dawn chorus. This is an example. This isn't plasmospheric hiss. I didn't have any, you know, I did have hiss, but it sounds very much like the solar flare radio blackout. It's slightly higher frequency stuff, but it's still just, you know, it's not as pretty as dawn chorus. And you'd be hearing dawn chorus as well, especially during the recovery phase of the storm. But this is, dawn chorus is from, believe it or not, from particles in the radiation belts being scattered into the upper atmosphere. And that happens too. And it makes a beautiful sound. Here's this one. So did you guys hear all that? Was that good? Hear birds chirping, exactly. Cat calls, there you go. So imagine all of that, all while you're trying to just make a phone call. So it should, guinea pigs, how cute, I've never heard of that. Yeah, dolphins, right. Neat stuff, huh? Sounds like your truck AM radio. Well, sometimes it may be. And so when you have a Carrington class event going on, even ones that aren't creating, you know, these massive geomagnetic storms, you could get stuff like this. So they create nuisances, right? As well, it's not something you couldn't wait out or something that you couldn't get through. But imagine if you had and this is my concern, that very few people talk about. Everybody thinks of terrestrial weather as terrestrial weather, and space weather as space weather, and never the twain shall meet. I worry about when the two do. That's my big fear. Imagine if we're having a hurricane or something, and there is some evidence that we're beginning to see that, you know, hurricanes can get intensified. Winds and potentially lightning can be intensified during inclement space weather, just simply because you're having dumps from the sporadic E regions into these clouds. And so it's an electromagnetic interaction, and there's a lot more work needs to be done in this area, but gravity waves are seeming to be playing a role. But I'm beginning to see a little bit of work done in this arena, which is nice. And at any rate, but even if you have, let's say, just a hurricane, irrespective of whether it's being intensified by space weather, the idea of having that hurricane then cause power outages and cause cell phone outages and cause, you know, infrastructure outages, so you have to swivel and use backup communication like amateur radio, right, or these other forms of communication that are you know, were given up, were from, you know, were relegated to the second tier of communication simply because they were so susceptible to space weather. And then you have one of these storms hit, and this is the radio noise you got to deal with while you're trying to, you know, save lives or be lifelines, communication lifelines to others, even if you're not relaying state official related communications. You're just trying to be humanitarian in your efforts. That's still providing an incredible service. And imagine having to try to fight this kind of radio noise, both from the sun screaming and the earth screaming. Wow, right? Painful, painful, painful. So those are the scenarios that bother me. Those are the scenarios I worry about, because those are the ones that we don't have mitigations for. We just don't. Everybody just keeps putting terrestrial weather in its own box and space weather in its own box, and they don't look at what happens when they create the perfect storm together. And we need to be paying attention to that and doing much more about that. Because this, like it or not, these technologies may be the technologies that we end up needing to rely on in situations such as that, because the infrastructure has been wiped out by inclement terrestrial weather. Okay, hopefully everybody understood this. Hopefully this kind of gives you a neat side of Carrington class events that maybe you hadn't thought would ever happen or would be relevant, but it is. Granted, it's a nuisance, but if it's preventing people from communicating, it becomes more than a nuisance, right? And it's not just the sun that screams, it's also Earth. Oh, yeah, I probably should have taken that one out. Okay, I'll go back and use that slide if I need to. It's just as a reference. So you would think with all of this that I've shown you, this big EMP, the L4 station, the L4 lines being taken out by the EMP, and power stations, power grids having problems, and radio blackouts, and what else did we talk about? Radio noise just from Earth and near Earth system being a total nightmare, to the point where people can't even talk on the bands at all. You would think, okay, the next thing, of course, is there's going to be gorgeous aurora everywhere, right? People should be seeing it all the way down to Singapore. Well, it turned out the only place we really saw aurora was near the South Pole. I looked and looked and looked for newspaper articles, any type of news about this event in anything, and I think I found barely one that wasn't even worth mentioning. Outside of that, no reports anywhere. This storm, literally in terms of the public eye, went completely under the radar. And why? No real aurora. Now, remember we talked about DST having only gotten to minus 125 nanotesla, and it was a very modest storm level, right? And the auroral activity, if anything, was just sporadic. It really wasn't record-breaking. In fact, we've had more active electrojets, the AE, anybody knows the AE index, which I'll show here in a sec, right here. We've seen 1500 nanotesla this year, multiple times, from our G3 level storms that we've had. I think one of them got to a G4, right? Got to a KP of 8. I think, I can't remember, I have to go back. I think I might have had a plot or two that showed KP for this storm. It was hovering mainly at 8. It might have reached a KP of 9, so a G5 level for 2 seconds, and then back down right when the EMP was hitting, but outside of that, no. It was really a modest storm. So here is the AE index, as a matter of fact, and the only time you can see it was really off the charts at this short period, both the upper and the lower indices that make the AE. The AE would be the subtraction of these two, so basically the envelope of these two, the upper and lower. So that's AE. That's about 1500 nanotesla. And that just happened during, basically, you can see right here is sudden storm commencement. This is right when that bumper car hit. So it was really just during that period, and then it really calmed down quickly. In fact, when you take a look at from Akasofu's work, this is a legend, this name. I studied some of his work when I was cutting my teeth as a grad student. He actually did a really nice little analysis where you get to see red aurora right here. This is from the southern, where the observations from the southern pole, which I'll show you in a second. But where there were times of red aurora, where the aurora was active, and where the aurora was moderate. Okay, so you see there was very active aurora right when the EMP hit, right, which makes sense. I mean, you're changing so much stuff and you're shooting electrons down the poles, even if you're not doing a lot of active auroral current building and peeling back and eroding of flux, you're still shocking the system so dramatically that you're going to get aurora. It's just not going to last very long. And then there was nothing. So this is right at the end of August 4th into the 5th, and then we go into the 6th and on down. Nothing really as the fastest part of this CME. Oh wait, my fault. This is all August 5th. I was like looking at it going, wait a minute, that's too many days. So this is all August 5th into the 6th. So the 6th is when things calm down. Okay. So the first part of this thing, you get that tiny bit of aurora right away for a very short period of time. Let's see if I can read what the time ticks are. Oh, are they an hour? 24, 8, 4, 5, 6. No, 2 hours. They're hour ticks. So this is August 4th, right? August 5th starts here, right? And you have the whole day. And then these ticks are 2 hours. Unless I've read it wrong, but I think I haven't. 24. Old papers, man. They're like these little numbers on this big plot. You blow it up, you still can't see the numbers. They're too small. We didn't get good at that until later. Most of these plots are hand-drawn, by the way. Looks like it's computer-generated, but a lot of the ones back in the day were definitely hand-drawn. And so for a few hours afterwards, you got no aurora, and then the aurora went to a moderate, just kind of meh, right? And then at the trailing edge, when you actually got another enhancement, you can see just at the lower, you actually had the lower electrojet being more intensified. Here it was more the upper electrojet, so closer to the pole. That was what was being really intensified, and then it didn't even get down very much into the lower areas until this one. And that is when we got some red aurora, which is oftentimes what we see. We see, even with storms today, you'll see red aurora, the storm aurora, during the recovery phase as things are beginning to calm down. And then it stopped, and you get a little bit more, and then it stopped, and it became like this sporadic thing. But it all stayed at pretty high latitude. In fact, when you look at this, this is 500 gamma. So this is 500 nanotesla. And remember, I always talk about the rule of thumb for substorms, not even a geomagnetic storm, but substorms for people at high latitudes to see aurora, is that you have to have a deviation of about 500 nanotesla. Well, look at this. Most of this period, you're barely peeking over that 500 nanotesla, right? I mean, even the envelope, if you looked at both, look at the AE index. This is 500 nanotesla, right? You're barely hovering at 500 nanotesla. It's barely enough for substorms during a lot of this period. So a lot of this stuff really may not have been, big geomagnetic storm stuff. It's just substorm stuff, all in through here. I mean, it's just crazy. This is just for a Carrington class event, you would never think the AE index would look like this. You just wouldn't. So what did they see? Meh. Pretty. Remember, this is at the South Pole, right? And they talk about, I think this was at 200 kilometers at the very, very edge. And they did see that the aurora did go southward, did go equatorward of zenith at the South Pole. So this is in Antarctica. They did see it go equatorward, which means the aurora disappeared off the edge. But that's only about 200 kilometers south, or north in this case, north of the South Pole. And it didn't happen very much, as you can see. You got it here. There's when it goes to the edge. But it never completely disappeared. I mean, this side did. But it didn't completely disappear. And so this is the time periods that the aurora. Does this look like a Carrington-class aurora to you? Oh, I thought I had another one. Oh, that's right. That's right. I had this plot and this plate. These were two plates. So I have them all in one for you. But this is really the only real aurora I could find of this storm. Can you believe that? Now, maybe some of you are great. You can do a lot of digging and find more about the aurora, but this was it for me. And it was South Pole. And red aurora may have been a big deal way back when, but any more for us in the 21st century? With this, red aurora is easy. But imagine, just imagine, if this camera revolution had actually occurred back in 1972, right? We wouldn't have to rely on pictures like this, right? we would have actually seen it, probably seen it much further equatorward than was reported. But we didn't have anything like that. We could see subvisual aurora. But I wonder how different it would look, because I don't think we've had in the modern era a bumper car Carrington class style event. And how does the aurora look during the main phase, during the initial phase, during the main phase? Would it be the same kind of stuff we see? Maybe, maybe not. Sure be neat to have one. So as we continue, and I talked about this a lot during the last class, because people are blaming, for instance, the weakening Earth's magnetic field as to why we're seeing aurora at such low latitudes. And I think that's unfair, because our technology isn't what it was so many years ago, right? Our technology is this. And these cell phone cameras, the sensitivity of these lenses are so amazing that you can take a picture and because you can look in the sky and go, there's no aurora. And you say, all right, fine, I'll take a picture. You take a picture and you look at it and you go, oh my, and you freak out because what the hell is my camera seeing that I can't see? And then you sit there and go, because you think you should be able to see what the camera sees. But this is changing the game when it comes to how we track aurora and how we look at solar storms. So it's no longer a fair and a level playing field. The way we looked at Carrington-class event storms and the way we judged them based on where we could see aurora or where aurora was visible as that characteristic, that feature, that's no longer, in my estimation, that's no longer a viable feature. It's no longer a quantitative metric of a Carrington-class event. Because we are seeing with G2 level storms, we're seeing aurora clear down to, Utah, Los Angeles, not Los Angeles, but same latitude as Los Angeles. G3 storms, we're seeing it clear down to Amarillo, Texas. I mean, this is crazy. We're going to see it down at Singapore with a G4 easily. I mean, it wouldn't surprise me a bit. And with particle precipitation, we're going to start seeing equatorial aurora more often. So we're going to have a harder time distinguishing the difference when the aurora is subvisual, because it's going to look more and more like air glow, especially in the equatorial regions, because it's particle precipitation in such a way. It's not going to look like the auroral bands that come from the north and the south. But, those moving targets are also going to open up a whole new area of study. So, for scientists and citizen scientists alike. So I look forward to that. But because it's a moving target and it's moving so quickly for multiple reasons, our technology, our Earth's magnetic field changing, we really need to slow down when it comes to saying these events are scary because we see aurora. Because that's just not, it's no longer a viable thing. And we're just going to fearmonger. And I don't think that that's acceptable, right? We don't want to be doing that. So let me see where I am. Okay, I'm getting pretty close. All right, so I've got a little bit more. So here's some more thoughts of what this event did. We had, you know about this because of Starlink. We had upper atmospheric inflation, right? Drag on satellites, if there were any, in low Earth orbit at the time, and there were. But this particular one, because of the way it heated things so incredibly quickly, there was some modeling that was done by Jakia in 1973. And we also had estimates from satellites at different altitudes that we're able to kind of measure and then plug into modeling. And you can see in this plot here, we're talking about KP. So here we want to talk about KP, right? We're seeing KP of 8. Here's KP of 8. So right, G4. I don't know if it made it to a G5, but it was steady for a G4 at the early part of the event, and then it jumped back up for a short while. That's when we got that red aurora in the south, at the South Pole. But it just was driven far more by the speed of the structure than it was really by auroral currents dropping down to really low latitudes. Just the magnetic field shaking. Kp is an indicator of magnetic field wiggling. It's not an indicator of auroral zone, not necessarily just an indicator of auroral zone strengthening, okay? So we can absolutely get Kp being high and aurora being mediocre, okay? Because in this case, the driving was being done far more by the bumper car than it was being by actual geomagnetic, by a big geomagnetic storm, by eroding the flux and putting it back and pumping energy into the system that way. It was more like brute force. So outside of that, let's take a look at the altitudes of the ionosphere. We've got all these different altitudes, and what we're looking at is density. How much is density going up? You know, how much, because what's happening is that as you put all this energy into the Earth system, it inflates the atmosphere, heats it, okay? And so it's going to rise, and the scale height is going to increase. It's going to expand, is really what we're talking about. When the atmosphere, the upper atmosphere expands, what happens is that it goes up in density, okay? And that's what we see here. So at 300 kilometers, we're seeing a rise, a little bit of a rise. 390 kilometers up, we're seeing a bit of a rise. 450, we're seeing even a bigger rise. 600 kilometers, even a bigger rise twice, right? Mainly from the two big impulses here from the first the bumper car effect, which is the biggest rise in all of them, but then also by probably some southward field at the end of this, which is why we saw red aurora. But remember, we don't have magnetic field data, so we don't know. Or at least not much. We had some at Pioneer 9, but nothing at Earth, sadly. But even at 600 kilometers and even at 900 kilometers, now at 900 we're seeing wiggles, meaning dense and then less dense, you know, depressions in density, and then increases and then decreases. So you're seeing a wiggling of reverberation. And that's what happens when you start getting really vacuous. You're not going to have much density up there. So you're going to get a lot more of that pumping going on. Whereas down at the lower latitudes, you're just going to get increases and then you know, mellowing out, but not so much big decreases. So that tells you how vacuous the stuff is up here and how different the atmosphere is. But at 900 kilometers, that's incredibly high. You're still in low Earth orbit, but not by much, okay? But the increases are such that it's anywhere between a 500 to an 800, depending upon where you're looking, a 500 to an 800% increase, okay? So when we were looking at these different satellites, and you can see them here, Explorer 32, OVS-3, OVC3, or OV3, rather, Explorer 8, Vanguard 2, and Explorer 39. All of these different spacecraft are giving us data at these points, showing these variations. During that period, right, the fifth through the, basically the 5th through the 6th, you had, you're having a delta T, a change in and I don't show the temperature, but you're having a change in the temperature of the atmosphere up to 500 Kelvin difference. Okay, and again, it's because you're inflating the atmosphere, and it's going to expand when you're putting energy into the atmosphere, and it's going to expand when you heat it, right? And that's what is driving the density change, because as you expand that atmosphere, you're pushing more particles up. As you push more particles up, it gets more dense because what was not there before is now there, right? So you're just literally inflating everything, and that causes drag. A similar storm in 1967, which we'll talk about maybe the next time, that was another very interesting storm. Not as much data about that storm, but I'll see if I can dig some up more than I have. But that storm cost basically NORAD to lose half of their catalog of low Earth orbiting satellites due to atmospheric drag. Sound familiar? This is why I said back during solar minimum, back in 2019, I said Elon better not launch his satellites into 200-kilometer orbits to then, you know, orbit raising from there. So that's not going to work. He's going to have the satellites falling out of the sky. And people laughed at me, but they didn't know. I knew this story. I saw the analysis done at Aerospace. I know what happened with this. So I knew they'd fall out of the sky. Right? So to me, I just let people laugh. Yeah, you can laugh at me, go ahead. I know what I'm talking about. And sure enough, it happened, didn't it? So imagine if we had one of these happen. Imagine the impact on radio communications and satellite-based services if this happened today. You're talking 500 to 800% variation in density. Shall we refresh our memories? Right? Right? Do you guys remember this? Wasn't that long ago. Now, analysis has been done on this event since the fateful day that SpaceX put out their thing saying, whoops, it looks like a geomagnetic storm caught us. And there's been several that's been done. We had Dang et al. do a nice paper. And their paper, and I'll show a video, their paper talked about a 20% increase. And they actually even, Space Weather was nice enough to give us a little, and I'll let this play, to give us whoops, that's not what I meant. Space Weather was nice enough to give us a nice little document of showing how they use the TIG or GCM model to mimic these little hot spots. And so here is geographic latitude, here's geographic longitude, so this is basically all of near space. They don't have a map underneath it. But they're talking about percent change in density. And you're seeing the 20%, sometimes you'll see as much as 60% in these what they called hot spots. And the Starlink satellites flew more in this range. And so it didn't really hit, they didn't cross through the depth of these hot spots. And this down here is the magnetic field direction and intensity at the Earth. At L1 during the February event. So you're seeing really where the storm occurred, which was mainly down in here when the field went really southward. But you're still seeing these hot spots that get built up during the period of February 2nd to almost February 5th. And they say 20% difference is really what these guys flew through, and that was enough, that 20% change. Well, okay, that's definitely shows us something. But 20% change? I don't know. That's pretty minor. However, Sui, who you might know is a NOAA SWPC colleague, and also she runs the team at SWPC that does the WAM IPE model, right? And you'll see a picture of it in a minute. She did another analysis. She and her team did. And I know quite a few people on this, and wonderful people. And Howard Singer, for example, is a great, Rob Steenberg is really awesome. These guys are top-notch scientists, very good at doing operational forensics of anomalies, satellite anomalies. So they've been working with SpaceX for some time, and Sui in particular, Sui Feng. And she's a rocket. I just love her to death. At any rate, just a really cool person. Here, you might recognize this. This is, if you go to the Space Weather Prediction Center, you can actually see this WAM IPE model. And thank goodness we've been waiting for this particular model for this data product for quite some time, because one of the things that it shows is the neutral density, right, at particular elevations. And in this case, she's got one at 210 kilometers, exactly where Starlink was launched, right? And her analysis, or their analysis, showed about a 50%, a little over 50, like 50 to 100. Actually, I think she said higher than that. Now, 50 to 125% increase. Here, this maxes out at 50, so it saturates. You can't see, but here you can see the hot spots coming in, and that's very similar to Dang. Dang had a hot spot here too, down in this area, but not 20%. Now we're talking 50 to 125%. Okay, yeah, I get it, right? That we got to keep that in mind, that maybe that's around the area, but even that to me seems modest, right? But think about it. If 40 Starlinks fell out of the sky at 210 kilometers because of a 50 to 125% change in density, what do we see? How much of a change? 500 to 800% change? And how far did that go up? Not even at 210. 210 was lower, right? So there'd be a bigger change even down there. But you're seeing an 800% increase at 300 kilometers. What does Elon park his vehicles at now? 320? Do you think he would have been immune? With an 800% change at 300 and a 500% increase in change in density, or actually you probably had a 500% change at 300 because that's where the smallest is, and an 800% increase here. Do you think he would be safe? And how about the Starlink satellites that are in orbit in operations right now at 450 to 500? Do you think they'd be safe? This is after their orbit has been raised to their operational orbits. Do you see why NORAD lost so many of their catalog? Carrington class events are no joke. It will absolutely sweep the Starlink constellation out of the sky all at once. Is that something that people had to worry about back in 1972? No, because we didn't have that many. We do now. Do you see how we begin to build in our own susceptibility to Carrington class events? And what was important back then with power grids and all that kind of stuff, and may still be important today or may not. Not nearly as much, because we have lots of other technologies that HF, for instance, we don't rely on HF nearly like we used to, right? So we've built ourselves out of that susceptibility. But now we've built in a new one with this. So now we're going to be raining satellites from the sky if we're not careful during a Carrington class event. Did anybody expect that? Probably not. Do we have mitigations in place for this? Not on your life. Do you see why my thoughts go in a different direction when people talk about Carrington class events being a planet killer? It's not a planet killer. But it could cause, you talk about raining cats and dogs. So give a whole new meaning to the phrase raining cats and dogs. Oh, and Starlink isn't alone, right? Don't we have OneWeb going up, right? O3b, the other 3 billion people who don't have internet. Don't we have quite a few constellations? Don't we have a lot of geospace constellations going up that just want to look for civilian use of photographic information? We have tons of civil and commercial vehicles going up because it's easy. CubeSats access to space is getting easier all the time. People are creating massive data sets. Wonderful. But what is this satellite CubeSat revolution? Where is it taking us? And what kind of new susceptibilities to these big extreme events are we building in? And it's not just a matter of, oh, poop, we got to add more gas for orbit raising. Because there could be a very good chance with something like this that you could have your little spacecraft on full throttle and it's still coming down. Okay. See why I don't worry about the Earth's magnetic field so much? Here's another one, guys, radiation storms. Now, this will be coming close to the end here. So radiation storms during the 1972 events, boy, they were interesting, very, very big. Here are, let's see, which is this? This is Explorer and IMP, the IMPs, IMP 4 and 5, I believe IMP 4 and 5. No, IMP 5 and 6, my fault. So the IMP spacecraft were very, very well known. I used IMP 8 spacecraft for solar wind data as a grad school. That tells you I was just a little bit older. It dates me probably pretty intensely. But it lets you know what kind of information I used. As you can see here, this is a diagram. Now this is from, I forget who this is. This is Cole and Bostrom and Williams. So John Hopkins, APL, and NOAA. This is a diagram of showing showing where Earth is, and I think are we X? Yeah. Okay. So we're looking down at the North Pole. Sun is over here, right, shining on us. And so the reason for this was just to show where the orbits were in the plane. So you had IMP, this is IMP 5? No, IMP 6. This is IMP 6. IMP 6 wasn't necessarily out of the Earth's magnetic shield, but it was close. It was in the magnetopause region, or magnetosheath region, which means that it really had a really good exposure to the particle environment. Okay. Now, IMP 5 was clear out in the solar wind. So it was getting the onslaught of the particles without any shielding. The shielding comes from inside the Earth's magnetic system. So that's why they showed this, was because they want people to know, they want, obviously everyone to know where the spacecraft are and when shielding began to take hold. So any passes down in here, you're not going to get, especially down in here, you get a geomagnetic cutoff. You're not going to get any, nearly the intensity of particles that you get outside. So that's why you see some of these dips and stuff in here. And I'm not going to go into the details of all of this because it's not as critical. I want to focus on the most important parts for our conversation. So yes, of course, the 1972 events had, big solar flares, a big fast CME, big radio noise, and of course a big radiation storm as well. Several, actually. But what was interesting about this radiation storm was that if you look at it, and these are the different data with different energies. This is energy of greater than 10 MeV. This is greater than 30 and greater than 60. And IMP 5 and IMP 6 data, you probably can't tell which are stars and which are circles, but that's what we're looking at, stars and circles at different energies. But what I want you to focus on is the IMP 6 data with the open circles, okay, greater than 10 MeV. Now, greater than 10 MeV means they're very penetrating, and these are the level that if the flux, meaning the amount that comes through a detector in a particular, in a certain amount of time, if it exceeds a certain threshold, then that's when you start going into these, what we call the S scale of radiation storms. So I think I might even have it on here. Yes, good for you. So here's the S scale for the radiation storms. And you can see you've got 10 to the 0, so 10. Basically 10, what they call solar flux units or particle flux units. And that's an S1. And if it goes to 100, that's 10 squared, then it's an S2. If it goes to 1,000, that's S3. Okay, 10,000, S4, that's 10 to the 4th, and 10 to the 5th is S5. Okay, so that's why I just want to give you an idea. So an S5 is a very rare. Okay, you don't get this, maybe one per cycle or so. Okay. If you take a look, you can see these protons, 10 to the 1st, 10 to the 2nd, 10 to the 3rd, 10 to the 4th, 10 to the 5th. Okay, S1, S2, S3, S4, S5. Look where the 10 MeV particles were, right at the hairy edge of S5. And this is IMP 6 data. This is the one that isn't out in the solar wind, it's out in the magnetopause, or I'm not exactly sure exactly when it was taken. I'd have to look again, I forget. But I'm just going to speed through this just a little bit because I'm realizing how late it is. I've taken a lot of time today. But this, nonetheless, is between an S4 and an S5 level. So very extreme. Okay. In fact, because of that radiation storm, and I think I have other data. Let me just check real quick. Am I going to show any other data on that? Well, I will. Yeah, but not yet. Okay. I wasn't sure if I kept one other thing in. But this radiation storm, remember, the Earth's magnetic system is such that it has holes, or has open magnetic field at the poles, at the north and the south. So anything from the solar wind can actually reach us in the north and the south regions much more readily. If it's energetic particles, let me say, be careful. Energetic particles can reach us in the north and the south much more readily than they can at lower latitudes because of the way our magnetic shield is. It's weakest at the poles and it's open to solar wind. So the particles can spiral on in and hit us. And we call those polar cap events, called polar cap absorption events, PCAs for short. But what happens when you get a ton of protons at high fluxes, high energies and high fluxes, hitting our upper atmosphere? Well, it ionizes stuff, right? One of those things that ionizes is ozone. Believe it or not, Carrington class events create ozone holes. They always have. In fact, radiation storms in general create ozone holes. They just aren't that intense, and they heal up pretty quickly. But the big events create big ozone holes. So if you get an S2, S3, S4, S5, the ozone hole gets bigger and bigger and bigger and worse and worse and worse, especially depending upon how long it lasts. Okay, so this has nothing to do with the speed of the CME. It has nothing to do with the geomagnetic wiggling or the EMP or any of that stuff. This is just the radiation storm. So if the CME had gone off a different direction, right, or a slightly different direction and missed Earth entirely, we still would have been dealing with this. Because radiation storms extend much, much further out than the big magnetic structure that can hit Earth, right? So if I'm not going to go back to it, but if I went back to that picture that showed that cute little banana and that little umbrella kind of thing that we were talking about, the radiation storm is sitting out at the shock front in front of it, and it extends far beyond the edges of that visible, that little yellow umbrella I created, okay, that little yellow banana. And so we would be dealing with this, even if that Carrington class event had missed us entirely. It will still create an ozone hole. But here's the interesting thing. When Reagan et al. Did this paper, they were looking at this rigidly rotating hole that was created and how far it went down and how long it lasted. This is 38 kilometers above, they're saying region at 38 kilometers above, irradiated by the solar protons between 1300 and 2100 UT on August 4th. So when the radiation storm first hit us, because it hit us, the radiation storm hits us before the solar storm does, okay, right? Because radiation storms come faster. And if you need to know that, look at my Invisible Killer. I think I call that the Peace series, and that talks about how radiation storms are launched, what drives them, right? In this case, you have a strong shock. That's going to drive them to higher energies. So we had very, very energetic particles, okay? Particles that were 100 MeV. And I didn't include that plot here, but they were about 100 MeV or so. And very, very high fluxes in this case. But what did this do? Well, it actually produced reactions, catalytic reactions that caused free radicals, nitrogen and hydrogen free radicals. And this ends up causing a polar ozone cavity that rotated rigidly for 50 days. Because if you know what radical reactions are like, if you're familiar with chemistry, what a radical reaction, what happens is that you have someone who's an element or a molecule or whatever it is that is unstable because it doesn't have the right number of electrons. And so it scavenges and steals electrons from its neighbor. And so it now is fine because it got the electrons it needed to make itself stable, but now it destabilized that particular, its neighbor. And so that one now becomes the free radical. So it's not solving the problem, it's just passing the buck. And so the radical, that new one then goes and does the same thing, scavenge it from its nearest neighbor. And then it's stable, but now it created a radical over here. And so when you do that, you can literally rip right through molecules and stable things and create problems. And when you have something like ozone, which is 3 oxygens in kind of a very tense relationship, then triangles, friends and triangles, it never works, right? Pairs of 3, there's always 2 on 1, they always hate each other. Kind of the same thing with ozone. They stick together, but they're always at each other's throats because there's always one-upmanship and stuff. And so anybody who comes in to rip through that will literally destroy ozone very easily. It's not a super stable molecule. And so ozone got just destroyed during this. And sadly, it rotated rigidly, meaning it didn't shrink, it didn't heal for 50 days because this radical reaction just kept ripping through it. Every time it would try to heal, the radical reaction would just keep going and keep going and keep going until eventually it just kind of peters itself out because it combines with something that can handle it and not cause problems for ozone. But then after that, after it stopped growing or it began to heal, but it healed very, very slowly because the wound was so deep. And the simulations show that complete recovery took nearly 4 years. Can you imagine you thought chlorofluorocarbons, right? CFCs were bad. Try a Carrington class event. 4 years to heal that ozone hole. And even over Russia, and I didn't include this either, but I saw reports of it was very funny. even over Russia, the reports of the temporary night side mid-storm, basically a sporadic E layer, because this hole and the radiation storm was so big, the particles either convected down to lower latitudes, or the radiation storm actually just opened, probably convected down to lower latitudes, or the showers were just so intense that they convected down. And so over Russia, you actually had sporadic E layers. That's how penetrating these particles were. They went clear down to the E layer. So guaranteed, it's events like this that could intensify. Thank goodness hurricanes and things only happen in the tropical zones, because if we had lots of hurricanes or lots of storms in the high latitude zones where all of these particles, all this charge was being deposited, goodness, it would intensify storms pretty crazily. So, that's one nice thing for having the terrestrial weather storms being only at low latitude, that they're kind of isolated from these effects. Except, of course, in the South Atlantic anomaly. That's obviously why we have a ton of lightning down there. You ever notice the biggest amount of lightning that we have on the planet is right in an area right over a lake in South America that's sitting in the South Atlantic anomaly? Doesn't surprise me. Doesn't surprise me a bit. Okay, so intense issues just when it comes to our upper atmosphere, right? Our neutral upper atmosphere. We have big, intense things that happen with Carrington class events. Strangely enough, it's not the only thing that it happens to. It doesn't take a Carrington class event to create an ozone hole, but to have one that lasts this long, yeah. But what about radiation storms at the moon? Does anybody say Artemis? Anybody think about Artemis? I sure do. So here's a couple papers. There were some studies that were done. We had Renee Medrano and Freeman in one, and here is who is this? Moore? Yeah, Moore and Resmer. Different instruments actually were on the moon at the time. We had Apollo instruments there, and as you can see here, they're showing a picture of in this case the Earth's magnetic system. Here's looking down at the North Pole. The sun is this way, and you're looking at the moon orbit. That's what this is. And so they're showing the date of where the Apollo missions were, and in this case, the look angle of that particular particle instrument. Because a lot of these particle instruments have to have look angles. They can only capture particles that are coming in at this particular angle. So if particles are slamming me in the back of the head, I don't notice it, because I've got my catcher's mitt out here. It's like I'm a baseball catcher, right? And I've got to catch the ball. But if the ball's going to hit me in the back of the head, I didn't even notice it was there. So that's the same kind of idea. The catcher with the catcher's mitt is looking this way. Okay. In this case, because I'll show this data, I like this plot better. This plot is terrible to me. So I like this plot. That's why I'm showing it. I'm not going to show the data from this. I'm just going to show this because we're short on time. But you can see Apollo 12, 14, and 15. They had multiple instruments, and these were the look angles of these instruments pointing, and here's the different days. So you had July 31st, August 2nd, If I were to take this plot and kind of meander it so that it looks similar, right? So that's why I like this plot, because it actually shows the moon, right? And it's a simpler look angle, but you can see that the look angle of this, if you had to take a look at it, it looks pretty similar to the look angle of Apollo 12. Okay, so these instruments have catcher's mitts looking at slightly different directions, but they're all sitting on the moon. Okay, but this gives you an idea of where the moon was during this solar storm, when the solar storm hit here. And so the radiation storm mainly was coming from the sun this way, or coming from the sun this way. Well, no, straight from the sun. What am I thinking? A little bit of curving around with the magnetic field lines, but still, nonetheless, in general, without getting too specific, it was coming in this way. So most of these catcher mitts, right, the stuff was hitting the back of their head, right? It wasn't really necessarily hitting right where you'd expect it to, okay? Now, people could argue about the backside of the shock. Okay, fine. But I'm only bringing this up. I don't want to get into the minutia of the details. I want to just talk about the fact that we had very strong radiation storms. This is from Apollo 12, this is Apollo 14, and this is Apollo 15. So Apollo 12, which is the one that was looking toward the CME, mainly, right? Especially in August 8th, but in August 4th. Yeah, August 4th, right? Looking toward Earth, okay? Looking partly sunward, my fault. Looking partly sunward, okay, during this period. It's going to get the best chance of getting the radiation storm that's coming from the sun. And sure enough, on the surface of the moon, bam, it gets hit hard. And it's a log of counts per second, so we can't translate it into actual flux, because counts per second, it's not exactly the same. We don't know the geometric factor, so we don't know how big the catcher's mitt was. If we knew how big the catcher's mitt was, we could then translate into what the flux is, but we can't because of that. Doing particle measurements, it's a little bit tricky how you translate it. So you can't just take it, you just take it at face value that we had large and very fast rising particle events at the moon during that period. Now, lucky for us, even though we had Apollo 12, 14, and 15, we had just finished a mission on the moon. And some of you who've been in my classes have recognized this. We had just finished Apollo 16. Okay. Luckily, nobody was on the moon at this time. The instruments were, and they were able to get a really good reading of what any astronaut who had been on the moon in the Apollo dugout, where they would have been dealing with. And remember, before you poo-poo us as a species, we didn't know much about storms at this time. We didn't know that much about CMEs. We didn't know that much about radiation storms. So we didn't really know what we were flying into, so to speak. Right? And it really was pure luck that, in this case, we were not on the moon at the time. Because when you look at this chart, here is from 1968 through 1972, 73 really. It's a plot of radiation level, storm level, and this is done in a fashion to make it, takes the numbers out but makes it easier to understand. So here's annual natural exposure is where this line is for a human being for radiation storms. Annual exposure for a radiation worker is up here, so that includes people who work in nuclear power plants or even pilots that fly commercially. They're considered radiation workers. Here's short-term radiation sickness, it would be at this line. And then here's fatal, and that's the red line. Vertically, these are the times of the Apollo missions: Apollo 7, Apollo 8, Apollo 9, 10, 11, 12, on and up. And look at this. See the blue line? We miss. Other than this one, we missed basically, which is a very low one, right? Which is hardly, not even the annual exposure for a radiation worker, hardly noticeable, barely above baseline, right? An annual natural exposure. We missed every single one. Look at that, just barely missed this one, which is still only barely above the annual exposure for a radiation worker, right? So this would be one dose, one mission would get you that exposure. Right? Missed it again, just barely. Missed it again. Okay? Missed it again. Here's the Carrington class event. Where does this line go up to? Past fatal. See that? So that radiation storm that we just talked about, as it was measured on the moon by the detectors that were in the muck themselves, the detectors did okay, because they were designed for it. Humans, we're the soft parts. We're not designed for this. Had Apollo 16 occurred in August instead of March, had Apollo 17 been moved up a year or half a year, and we were on the moon at that period, the astronauts would have not made it back. They might have died right in their spacesuits. How do you think the space program would have looked? Think we would have had a space program? Think we would have been much more terrified of exploration, human exploration in space? By the way, 1989 event, which we have yet to go over, one of the Halloween storms that we have yet to go over, also would have had doses like this. Because this one, although strong, does not take the gold medal when it comes to solar energetic particles. That gold goes to the 1859 event. So it's not the biggest one on record. But even at that, it was enough. We've killed them right in their spacesuits. See why I'm nervous about Artemis going up to the moon during solar max? Much more worried about them. Okay, so what did this storm do? Consequences of the extreme August 1972 solar and geospace storm. Well, we had multiple X-class flares and an X-20 class with gamma rays, and we had white light solar flares. So big, made the headlines, absolutely. Intense sudden atmospheric disturbances, these are the magnetic crochets that caused major changes in our upper atmosphere over a short period, just because of the solar flares. Long duration radio communications blackouts. We did have radio bursts that went up to 1 gigahertz. I didn't share them here. But not only did we have these intense radio blackouts in the HF band, but they went up as high as 1 gigahertz. It didn't matter all that much because we didn't have a lot going on at 1 gigahertz back then. But now we have satellite phones. We have L-band, right? We have lots of GPS, GNSS, lots of satellite communications at those frequencies. I bet you it went past 1 gigahertz. We just may not have had the equipment to be able to gauge it. It's definitely the fastest solar storm on record, so therefore just in it of itself would classify it as a Carrington event. Deepest forebush decrease on record because of that bumper car effect. Detonated magnetically sensitive sea mines off the coast of Vietnam. Disrupted North American communications, that's the Bell network, their lines and power grids. We had extreme radiation storm in the near-Earth environment that produced an ozone cavity that lasted for weeks and didn't heal for 4 years. Could have been lethal to the Apollo astronauts had we been there. Caused an 800% inflation in the density of the upper atmosphere. But the geomagnetic storm was yawn-worthy. The one thing that everybody is so petrified about. Oh, the Carrington class event's happening. It's going to blast us in the dark ages. All our transformers are going to melt. No, not this one. An EMP has a hard time taking out transformers. If they can react and handle it for a short period of time and survive it, and then the field goes northward, they just go, okay, that sucked. The biggest issue with EMPs is that the power grid operators have to be on it. Why? They got to turn off the relays. They got to turn off all the alarms. That doesn't remove stuff from the grid. That's the biggest problem that we have with EMP, is that the grid operators have to be able to say, no, ride through it, we'll be fine. If they can ride through that short 2-minute period, they'll be okay. But if they start taking things down, taking parts of the grid offline, now it puts a heavier burden on the other parts of the grid. And if that Carrington class event does end up rolling into a geomagnetic storm, now you're really in trouble. But if it doesn't, if it doesn't fry you in the first couple seconds, basically, you're good as gold. So does this mean that this shouldn't be a Carrington class event? No, absolutely does. Look what it did to the military, right? Look what it would have done to astronauts on the moon. If the astronauts had been there, trust me, we wouldn't be thinking about the 1859 event. This would be our standard candle. 1972 would have been it because astronauts died, right? That's what we would have been thinking of. How about if Starlink had been up? If Starlink had been up in August of 1972 and the satellites had been raining from the sky over the next week because they all came down to 320 kilometers like that, and then the rest of the atmosphere took them out over successive days of deorbiting. And so it was raining satellites for a week or two. And every day you'd hear of several different, burn-ups in the sky or possible debris. Trust me, this would have taken over the #1 spot in our popular culture, despite no aurora, not really. So do you see how I'm trying to help define, trying to take, get you rid of the junk food that you've been eating from Hollywood and these crazy YouTubers on social media and all the fear-mongering, the fear porn that goes on, and try to build you up with much more healthy understanding of what Carrington class events are and why Pete Riley can, with a smile on his face, say, yeah, we've got a 12% chance of getting one in the next decade. And it's not causing him to literally say, quick, fetch me my brown pants. It's because there's all sorts of different types of effects that a Carrington class event can do. And not every Carrington class event is going to do everything to you, to Earth. Matter of fact, most likely it won't. There are certain things that each Carrington class event does. And sadly, you can't predict that a priori, because we don't even know which side of the Earth is going to be, on the day side or on the night side, when the dang thing hits. We can't even predict these things nearly as well as we'd like. I wish we could, but that's 50 years, 100 years perhaps in advance, until we get more satellites and spacecraft out there to be able to measure that 99 million miles between the sun and the Earth before the thing hits us. We're blind for that period and can just do guesswork. We see it at the sun, and then we got to sit there and wait that intervening space, not knowing what traffic it's going to hit on the way, to even know when it hits us. And half the time, it's not even just that causes the problems. In this case, this thing could have missed us completely and the astronauts still would have died. Why? Because of the radiation storm. So does a Carrington class event even have to hit us to be devastating? No. But it does have to be lucky, or in our case, unlucky, right? But this hopefully gives you a much better feel for why this kind of nomenclature and this kind of definition really has no place. I don't even know how to process this, because it doesn't fit in with any of the quantitative criteria that we have to really use if we really want to understand what Carrington class events are and how they affect us. This is just fear-mongering. So again, taking a look at the Carrington class event Olympics, well, now we've talked about the 1859 pretty intensely, and now we've talked about the fastest one on record, the 1972. But look at this, we have Halloween storms to go. We have all sorts of the 1872. I hope I can find any data on that one, but that's going to be hard. The 1989 event we'll talk about, the railway one in 1941. We'll talk about ones that are more classic, but we'll also talk about the 1967 event, which was, to some degree, a bit like what we just saw. So we've got a few more to do, and maybe on Patreon I will ask you guys, what ones do you want to talk about? But by that same token, as a parting word, the 1859 event, just like I said last time, the 1859 event does belong where it is as the defining Carrington class event, because in the Olympics, in the Carrington event Olympics, it really did medal in every single event. It may not have taken the gold in every event, but it medaled, got the gold, the silver, or the bronze in every single one. And there are very few events that have done that. And they deserve to be called Carrington class. But the 1859 one was definitely stood out. Okay, so we will continue to call the 1859 one the definition, the one to beat. But the chances of us getting an 1859 event again are much, much lower than the 12% Pete Riley mentioned. Okay, so take heart in that, because that is more the truth. And that's it, guys. This is a bit of a long one this time, but hopefully you enjoyed that. And yeah, I forgot to mention this, right? The August 1972 event, it's no exception, because it was hard, it was tricky to define the Carrington class event, even from the 1972 event. It's no exception, but its impacts to society cannot be overstated, right? It will forever be far more than the fastest event on record, because scientists have a tendency to look at it just as this. So here's kind of a nod to the public eye, right? This thing was very intense, and it had a very lasting impression. And if it had happened today, the impression would have been insane. Or if it had happened during one of the Apollo missions, the impression would have been unbelievably devastating and unforgettable. But scientists have a tendency to say, well, it was just the fastest one on record. Right? They have a tendency to remove the human element. And I think we need to put it back, but I think we need to put that human element in its place, right? It's something that's important, and the impact on society is important, but it's not the only way we should be defining these Carrington class events. We need a balance. Okay, so I think that is now it. That was my final statement. Hopefully this was good. Did you enjoy this one? Even though it was long? We got through a lot of charts today. We got through like 36 charts, which is a lot for one of these mini courses. The next one is the SCOVE event. Oh Lord, I hope not. If I create a Carrington class event, we're all in trouble. That's funny. Runs with scissors. Yes, your name is just as funny as that, so I can see why. You've lived up to your name. Okay. I'm missing some of this stuff. Thank you for your all-time space. Oh, you're very welcome. Appreciate that, Iami. Did today's solar storm? It's moving too quick. You need to watch this again, Terry. Yes, please. I do these as once a month, so feel free to to go back and rewind and take breaks and look at it again. It is kind of like drinking from a fire hose. Hopefully not too much. This was see the whole truth. This was a great class and overview. Good. I'm so glad you enjoyed it. Okay. Yeah, Starfish Prime. That's some interesting. Starfish was an interesting mission. Yeah. I mean, it's declassified, thank God. But I don't like nuclear detonations in space. I can't believe you've talked for 3 hours and 47 minutes without coming up for air. Thanks, Mike. That's so kind of you. Yeah, well, this stuff is interesting to me, and I wanted to be able to give you guys a synoptic view, a comprehensive view of this event. Q&A, well, yeah, I mean, I pause at times to do a Q&A, and I'll do a Q&A now if you'd like. So that's what I'm looking for questions. This is what I always do. I take breaks and I do question and answer during the breaks, and then at the very end I do Q&A. So thanks, Jerry. I'm glad you enjoyed it as well. On the 5, we ignore what earlier cultures understood without having to know why. Earth, sun, moon interact as one. Scientists can connect the dots if the rest of us work together. Sans egotism and ethnocentrism. Agreed. It's hard to get over egos and empire builders. But there's a lot to be a lot of positives to be said, and looking back in the historical record and how societies have dealt with it, and even different philosophies, Eastern philosophies, for example, they have some amazing insights that we as a Western society, Western culture, have a tendency to forget and poo-poo, and we really shouldn't. So I fully agree with that. What happened on July 23rd, 2012? Oh, you mean the Carrington class event? A Carrington class event that missed us. It's just that simple. It would have been a pretty damn good one. Let's see, Nathan, bravo, I missed 60 minutes, but we'll rewatch while presented. Oh, thank you, Nathan, I appreciate it. Yeah, the Carrington class event in 2012, I mean, that's why it made such news. But sadly, the Carrington class event in 2017 didn't, and it clipped us. The reason why it didn't make the news is because Stereo B wasn't there to catch the dang thing, because Stereo B by that time was dead. But if Stereo B had been alive and we had gotten the big magnetic record of that one, I guarantee you that 2017 event people would know about. It's just what people are able to publish that lets you know, that inform you. But we had essentially three Carrington class events during Solar Cycle 24. Chris says, great job as always. Thank you. Appreciate that. This is one of the best, Mike says. Oh, thanks. I'm hoping you're liking this. It seems like you guys are really liking the Carrington lectures. So these are good. I should call them the Carrington lectures. 25 will peak probably spring to summer of next year. That's my educated guess. I'm a little bit behind Scott McIntosh, but not by much. I don't think it's going to peak in January. We're still seeing evidence that it's not like these lulls. We wouldn't be having a lull if it were Solar Max. I will never give up by ham radio because the satellite can be destroyed in a heartbeat. I agree. Amateur radio is the secondary, it's the backup communication system of the world, and also you're the Elmer to the Mars generation, because if people want to go colonize Mars, you're going to need amateur radio. Sorry. It's going to be different frequencies, but same physics. So hang in there. You know, there's definitely not going to be, you know, infrastructure for this stuff. And over the horizon communications, I'm not sure we're going to be able to set up repeater networks fast enough. So over the horizon is going to be important. Skywave is going to be important. When is the next Carrington event likely? You know, it's less likely in this cycle than it was in last cycle. And the reason for that is because this cycle is a little bit bigger. The hemispheres are behaving a little bit more in concert, the northern and southern hemispheres of the sun. So the chances of us having the really ugly magnetic field configurations that cause those really bad actors is a little bit lower than it was for last cycle, but not non-existent. If this had been even a stronger cycle, it would be less of a chance. But yeah, like I said, we had 3 Carrington-class events that occurred last cycle, or nearly 3. 2.5, as I call it, because the final one, it's kind of hard to tell if it was a Carrington-class event. It sure seems like it could have been. We just barely clipped it, so we don't know. It wasn't moving as fast as as a Carrington-class event at the flank, but we don't know about the apex. And that's, we just didn't get hit head-on by any of them. We got clipped by one, but the other 2 missed us. So, you know, what are the chances? Well, we had one back in April 23, or April of this year, that was on the far side. Once again, could it have been Carrington class? It was very close. It was very fast, very big, but we don't have any. We didn't have any spacecraft it passed over, so we couldn't tell. But they're around. They're much more common than people realize. Julian says, I joined along the mini course. I need to watch the first hour. Really interesting as usual. Thank you. You're very welcome, Julian. I'm so glad you liked it. Hey, you know, and if you have questions, ping me on Patreon. I'm going to go look on Patreon, as a matter of fact, in just a second for questions, for those of you who have not gotten your questions answered. Trespire says, are the utility companies addressing the known risk of solar flares? Absolutely they are. The NERC and the FERC, the National Energy Reliability Corporation and the Federal Energy Reliability Corporation. I think those are the acronyms. At least in the United States, and the PGM Consortium in the Canadian areas, those are the ones I know the best. National Grid, they've got their own. This is for the people in the UK. All of them do. And they work very closely either with the Space Weather Prediction Center here in the United States, or they work with the MOSWAC in the UK. So yes, they're very aware, and they've put in lots of things, lots of mitigating procedures, starting at a G2. So that tells you how on it they are. And that's part of the reason why we've not had like a 1989 event. That's why the 2003 events didn't take us out nearly like the 1989 one did, because we're getting smarter, right? Sadly, the green energy projects and wind power and solar power may be building some of those weaknesses back in our infrastructure, because there's a lot more relays and connectors and switches that are not space weather susceptible, or not space weather rated. So there's work that's being done right now, and research that's being done right now, that's actually indicating that is weakening the grid in terms of space weather being susceptible to big GICs. We'll see. Okay. Did we miss the predicted Carrington? It wasn't predicted. In 2012, yeah, that was the Carrington that went to it was July, I believe it was July, right? And it went to the sun's far side, sort of. It was 8 days off. It was actually to the west of Earth. But it missed us. But we've missed it. We've had several Carrington events miss us just recently over the past decade. It's not uncommon, guys. It's just not uncommon. If Mars's atmosphere is different than ours, propagation will be different. It is. It's extremely different. It's much more vacuous. And sadly, Mars is much more susceptible to space weather, especially radiation storms, than Earth is. Earth can protect us, and most of that stuff gets absorbed up in the upper atmosphere. But Mars, it comes all the way to the ground. So you might as well be standing on the moon. I mean, it's the same kind of thing. So that's another reason why I'm worried about Mars. We are going to have to live underground and come up for air, but we'd have to check the space weather before we do. I'm dead serious. That was, sorry. I'm alive serious. I'm just serious. But it's true. Okay. We are taking space weather mainstream, which is a great vision. Oh, thank you. That's sweet, Smash. Space weather is of increasing importance. That's why our channel covers it. That's true. Smash, they cover their space weather just like Matthew Shipley does. And I suggest you go and take a look at his channel. Smash, go ahead and put your link to your channel if it lets you. Mike and Jerry, he has my blessing to do that. And Matthew, if Matthew's on. I haven't seen Matthew on today. But yeah, anybody who is promoting space weather, you know, I appreciate you very much. And you're part of this army that we're all, you know, this community that we're building. Because we really need this information out so that Hollywood doesn't have a chokehold on us anymore. I mean, I'm sick of Hollywood and how their take on space and space weather. It just drives me crazy. Okay. Yeah, Bob, I agree. You are the other that has spoken out of love. I agree. And very, very passionate about space weather. Very good people. Nathan says, how would Carrington event likely affect RF propagation? It would deaden it. I mean, it depends. See, the thing is, it depends upon what part of the event you're talking about, right? Are you talking about the solar flare part? Are you talking about the radiation storm part? Are you talking about when the actual storm hits Earth, when the CME hits Earth? It's totally different. Solar flares, of course, and radio bursts and even radiation storms, they will cause radio blackouts. And in order to get over them, you have to go up to higher frequencies. With a radiation storm that happens at the poles, and it's really hard to get over those because that's particulate. So those are the polar cap absorption events, and those are really hard to get over. Radio blackouts, that's easier. That's on the day side of Earth. Okay, that only affects the day side. So if you're on the night side, no problem. Or if you're at lower latitudes, no problem for a radiation storm because you're not going to deal with it nearly as badly. But when a solar storm, when a geomagnetic storm occurs from the big solar storm hitting Earth, well, that's going to affect the night side. And sadly, switching to lower frequencies help. Okay, higher frequencies get pummeled on the night side. So it's a trick. In order to do well on the day side during big solar flares and radio bursts, which is probably happening during a Carrington class event, then you need to switch to higher frequencies. But then as soon as you switch to the night side, if there's a big geomagnetic storm going on, then you got to flip to lower frequencies at the one, then you know, like the top bands, and try to get through that way. But knowing your timing, right, staying alert of what space weather event is happening at any particular time will tell you which side of the Earth communication is going to work better on. And you just have to kind of, you know, use your savvy, your amateur radio savvy of knowing what frequencies you can use on the day side, what you can use on the night side, and what you can use on the gray line to be able to ferret out what is the best solution. But it's tricky, there's no doubt. Hopefully that helps. Okay, let me check real fast, guys. Yeah, let me check really quick on Patreon to see if I've got questions, because I know Spock's daughter, I love that name, Spock's daughter, she's asked me questions. Okay, load more comments. So let me look at two levels here. My question, Heidi says, do you think we see more X flares in the next solar cycle? Do you mean the next solar cycle, cycle 26, or in this solar cycle? A next solar cycle, I can't tell yet. Hang on one sec. Okay, just want to check, make sure there was no other. There's another set of questions, but I'll answer this one first for Heidi. If we're talking this solar cycle, I think in general we have a bigger chance of seeing more solar flares and larger solar flares than we did in cycle 24, which was the previous cycle. And the reason for that is because this cycle is more active, and so there's going to be the number of events we're going to see is higher. The number and the number of extreme events, bigger events, are going to be higher. But when it comes to big events like X 45, the chances of those are going down. Even though we didn't see any during cycle 24 at all that were that massive. What I think we saw in X, well, we would have had it not been occurring on the far side. The one on September 10th of 2017, which was the second of the two large, super large flares. That one was likely above an X10 because that was when a Carrington class event was launched. But it was occulted. It was an X82 from our perspective because it was occulted, meaning that the part of the sun, it was behind the sun's limb, and so you didn't really see the whole thing. You only see part of it. And so that then makes it a lower level than what it would have been. But I do believe it was above an X10, and a lot of scientists believe that as well. And then the other one we had, it was just a few days prior to that. I think it was September 6th, and that was an X9 something. So those are the biggest that we saw in cycle 24. And I think we could see more of those, near those level this cycle, but likely not until we get through solar max. Once we get really through the main part of solar maximum, and especially as we begin to start that downward, the slow descend into solar minimum, I think the chances of seeing the big flares will be higher. And Carrington class events, they can happen at any time, really. But a lot of them happen near the dying end of the solar cycle rather than the rising side. We rise to solar maximum quite quickly. We descend to solar minimum much more slowly. So just be aware, that in itself may be part of the reason, is because we have a longer time that we dwell in the declining phase than we have in the rising phase. And that in itself is going to make Carrington class events appear more often in a declining phase, just simply because there's more time we spend in it. It's really hard to say, and we don't have an ability to predict solar flares and the intensity of solar flares until we see the bad actor that emerges on the surface, and then we can give you probabilities, but which is kind of like prediction, but not quite that good yet. Until we start seeing these really big sunspots, which we haven't. Go back to the historical record and look at the sunspots in the 1950s and 60s. You'll see they're massive. They're unbelievable compared to the things we see today. I've seen much bigger sunspots in the solar record than what we have during today. That's why the idea of a micronova to me right now is just silly. We've seen far more active sun, and a micronova wouldn't, a big mega flare wouldn't just appear out of nothing. You'd have to see the sunspot emerge. You'd have to see the something strange going on with the sun, and we're not seeing that. The sun is behaving quite beautifully, to be honest. All right, hopefully that answered that question. Let me see what other questions we've got on Patreon. Okay, so okay, Jack Dolacourt. You said your August 24th forecast prompted this question, which you might answer at this month's or some future educational lesson. That's so kind. I understood you're saying that noise on the amateur radio bands was due to a lack of flares. Could you say a few words about the genesis of radio noise on the HF bands? Due to a lack of flares? No, not really. There's two things that cause noise on the bands in general. I'll say three. Should I say three? Yeah, I'll say three things. I'll break it up, one of them, into several parts. So the easiest one are radiation storms. Okay. Now, radiation storms, just like we talked about, they affect the polar regions. So these polar cap absorption events. So if you're in high latitudes, you're gonna deal with them a lot more than obviously if you're at lower latitudes. Or if you're an airline pilot, they hate them because as they fly over the poles, not only are they getting doses of radiation, but their HF comms goes out, and their navigation isn't so great either, unless they're using inertial navigation. So radiation storms are a real pain in the tush for lots of people, but especially aviators, because they use the polar route so much. But they do affect, like I said, HF communications and other frequencies, VHF, UHF, they affect a lot of those as well. So skywave is tough. But the more common one, of course, are solar flares, right? Because they can cause radio blackouts. And they do that in two different ways. The first way they do it, and the most common way, the way that we've known since antiquity, are through the radio blackouts from ionizing the upper layer, the D layer of the ionosphere. And that's because the energy of the solar flare, it's light, it's electromagnetic light, but there's so much energy in X-ray and gamma ray and all the high EUV, all the wavelengths of light that are absorbed by our upper atmosphere. How does the upper atmosphere absorb them? Well, it liberates electrons. Okay, you get photoionization. That photoionization means you get a lot of free electrons floating around in space. That causes more charge distribution. It causes more potential. The total electron content of the ionosphere goes up. And so that actually causes certain frequencies of radio signals not to be able to, they just get absorbed by those extra layers, or that thickening layer, let me say it that way, the D layer. So skywave ends up being not possible. So that's one way a radio blackout can stop communication. And then you get that noise on the bands that we talked about that you heard in that recording. The other way is through radio bursts. Now, radio bursts are actually the sun screaming. Okay, so when the sun is screaming in radio noise, it'll scream up into the gigahertz range. I mean, it'll scream up into the tens of gigahertz, if not 20s of gigahertz range. We've seen it, way up there. So it'll black out, because this is the case of the cricket near the train tracks, right? The cricket can chirp all along and be just fine, and everybody can hear it until the train goes by. And the train is so much louder than the cricket that it drowns out the cricket. Now, the cricket isn't getting injured, right? But you just can't hear the cricket. Well, the satellites are the cricket, right? And skywave is the cricket. And the train goes by, and it's just drowning out everything. So anything on the day side, because if you can see the sun, you can hear it scream. Anything on the day side gets drowned out by this screaming sun. But as soon as the train goes by and that solar flare dies down, right, you can hear the cricket again. So it's not like it's doing any damage to anybody. It's just screaming louder than you can is really the case. So there's two different ways that a solar flare can impact radio communications. One is to muck with the ionosphere. Another is just to literally compete with your ability to talk, like your loudness or your ability, and your ability to receive the satellite's loudness if you're talking via satellite. Okay, so hopefully that makes sense. So if you're on the far side, if you're on the night side of Earth and you can't see the sun, not only can it not ionize the ionosphere, so it won't affect skywave propagation that way, but also you can't hear the radio burst. So you're safe. Now the only thing you have to deal with are the radiation storms at the poles. So anytime things are flare active, go to the night side. Do your communication after the sun goes down. You'll find it'll be much, much easier and you'll enjoy it more, right? Until, of course, there's a big solar storm that hits Earth and then all bets are off. So hopefully that answers that question. Okay, let me get one more. I've got some from Spock's daughter here. Is there any yet consensus about the most likely time frame for a maximum of the cycle 25? Okay, yeah, I can do it. And second question, I read somewhere just after max can be expected several years, even more chaotic prior to max. Okay. Can you hear how high your California water was? We had 4.5 inches where we are. We had 4.4 inches, which, to be honest, people thought that we were going to, it's our first tropical storm. California's going to they're not going to know what to do with themselves. No, actually, we're a desert, guys. We know what flash floods are. So yeah, Palm Springs had some issues. Oak Park had some issues, but these guys have sadly they've dealt with it before because they know what flash floods are, and Los Angeles, our Los Angeles River did very, very well, and a lot of us were kind of laughing. I mean, the ones that weren't in these really bad areas, but all of us were scared that, goodness, this is going to be anything unlike anything we've ever seen. It ended up being something we could handle very easily, and yeah, it was hard. It was hard rain, but we actually had harder rain earlier during our last rainy season than we had here. So earlier this year, we've gotten much more rain than we got here during this tropical storm. So we feel, I actually gave me a little bit more confidence that our infrastructure, our drainage infrastructure is much, much better than we thought. And I think it's because flash floods taught us that, right? Being almost, essentially a desert community, Southern California is. We know what flash floods are. So, okay. So there's that. Now, regarding solar cycle 25, I had answered it before, but I will answer it again. Likely it's going to be in about mid-year 2025, or 2024 rather, mid-year 2024. The consensus that NOAA has was that it was going to be in 2025. Scott McIntosh and the NCAR crew believe it's going to be late 2023, January 2024, most likely. He feels it's going to be early 2024, but he feels that it could swing to maybe mid-year. I think definitely mid-year. I think on the late side it will be the later, the third quarter of 2024, but probably right around summertime. We're seeing issues, the sun right now kind of still quiets down. We do have a full band of active regions, but not all of them. They're not always active all the time. There's a part of the sun that still is not quite filled in terms of activity. So I think we're not quite there yet. But we are really close to seeing the multipolar sun. When we start having CMEs lift off of the northern and southern poles, very, very common, without it being an extremely common occurrence, then we'll be there. And as soon as we don't really see coronal holes anywhere near the northern and southern poles, I think we still have a little bit of a coronal hole in the polar region. So I don't think we're quite there at solar max yet. But we're probably going to have a double hump, right? So double peak solar cycle. We'll begin cycle 25 max sometime, mid-year 2024, and then it'll continue probably until maybe mid-year 2025 before we really start the decline. So we'll get a peak of activity. It might decline a little bit, and then we'll get a second peak of activity because the two hemispheres, the northern and the southern hemisphere, are not in line yet. So they're going to peak at different times. And so that hemispheric asymmetry is going to likely cause a double peak, and then we'll start a slow descent. So hopefully that answers that question. And did you have one other question? Shoot. Sorry, I forgot what it was. Oh, right. The declining phase of the solar cycle, is it more chaotic? No, it's not. It's actually much easier. And the reason why I say that is because that's when we start getting these coronal holes, these long equatorial, trans-equatorial coronal holes that are co-rotating with the sun. So every 27 days, like clockwork, you get solar storms. And it's really, if you want to be an aurora chaser, it's one of the best times to be an aurora chaser because you can plan almost a month in advance. It's really nice. I love it's my favorite time of the solar cycle. Of course, satellite operators' least favorite time, especially the satellite operators in GEO, because that's when all their satellites die. Because these recurrent solar wind streams are like pushing a swing, and it pushes, and if you're in resonance, it just keeps pumping up the radiation belts and makes them more and more and more energetic, just like you're pushing a swing to go higher and higher and higher. That's what happens during the declining phase. So satellite operators are pulling their hair out because they have so many anomalies, especially as we pass through the equinoxes. But it's just, you've got about a couple years of that, and they just hate it. But it is what it is, just weather, right? Just space weather. So hopefully that answers that question. And I think that's it, guys. If you have questions, I will, just so you know, as I will be watching all of this as time goes on, and I will look at even after this stream is over, I'll go back and I'll look at the comments you made. So if you are a person who wants your questions answered and you're a Patreon person, feel free to put more comments and stuff in Patreon. But I will definitely read your comments, and I will see how I might be able to incorporate the answers to those questions in my next lecture, okay? So hopefully you guys had fun. Looks like there's a lot of conversation going on. And I hope you find this informative. And yeah, stick around for the next one because we're going to be talking about other events. We might even be talking about events that are not officially Carrington class, but possibly should be. And we can discuss why they should have been labeled Carrington class events, but have not officially been yet. Okay. All right, guys, good. I hope you enjoyed everything, and I will talk to you very soon.